Hello, good evening everyone and welcome to this session on revision of entire thermodynamics in 90 minutes with me Vikas Sir. So everyone quickly join me for this session. Yes, today in this session we'll be revising the entire thermodynamics subject in just 90 minutes. We'll try to do that in 90 minutes. Definitely 90 minutes बहुत ही कम time होता है. It's very less time for revising a subject like thermodynamics, but definitely we'll try that. Okay, so quickly join me for this session everyone. Yes, right now we have Vimal. Hi Vimal, very good evening. Srikant Bodhi, good evening. Vikas Yadav, good evening. Mohit Kundu, good evening everyone. Good evening, good evening, good evening everyone, and welcome to this session on revision of entire thermodynamics in 90 minutes. In the crash course series going on the YT channel, this session is very important. Hi Bunny Kaushik, very good evening. So everyone quickly join me for this session and please share this session to many people as possible. जितना हो सके आप share कर दीजिए session को. Please share this session, and also those who have joined me for this session, please like the session and also subscribe the channel, press the bell icon. Yes. So everyone, those who have joined me for this session, please like the session, share the session, and if you have not subscribed our channel, please subscribe the channel, press the bell icon. Nishit Yadav, very good evening. Abhijit, good evening. Shivam Singh, good evening. So good evening all my dear students. Welcome to this session and Merry Christmas to all of you. Today is also the Christmas 2020. So आज Christmas के दिन हम लोग thermodynamics को revise करेंगे. जल्दी से सभी लोग आ जाएंगे in this session. I can see the strength is very less today. बहुत ही कम बच्चे आए हुए हैं. जल्दी से सभी बच्चे आ जाएं. जल्दी से quickly join me for this session. Yes, everyone, quickly join me for this session on revision of entire thermodynamics. So those who are preparing for GATE 2021, this session is definitely very useful for all of you, because today not only we'll be celebrating Christmas together, today we'll be celebrating Christmas with revision of thermodynamics. Yes. So Merry Christmas all of you, those who have joined me for this session. J.S. Srinivas, very good evening. Praveen Singh Chaudhary, good evening. Sarath Lal, good evening. J.S. Srinivas, good evening. Mohit Kundu, good evening. Akhilesh Khadse, good evening. Santosh Kumar, good evening. Arvind Balu, very good evening. I am very fine. How are you dear? कैसे हैं आप? So good evening and good evening to all my dear students. Welcome to this session on revision of entire thermodynamics in 90 minutes, where we'll be revising the thermodynamics subject. We'll be completing the subject of thermodynamics non-stop. I will not be stopping in the mid when we start the revision. So only discussion we are going to have is now, because after that, only thing that we'll be doing is revising the thermodynamics. Thank you so much, Kripal. Thank you so much, Kripal. Bharadwaj. Hi, Sudarshan. Satish Kumar, very good evening. Varun Tyagi, very good evening, my dear. How are you? So, good evening, everyone. Welcome to this session. And those who have joined me in the YT channel, please quickly like the session. Come on, guys. Quickly like the session. Please turn this likes to total number of watching. Right now, I can see 35 students are watching the session and the number of likes are just 24. Can we make this like equal to total number of views? Yes. And guys, if you please also share this session. Please share this session to your friends who are preparing for GATE 2021. आज अपने friends को Christmas का gift दे दो. Share कर दो ये session. सभी को share कर दो. Please share this session to your friends, to your colleagues who are preparing for GATE 2021. Just share this session to everyone. Okay? Yes. So my dear students, I will not wait much because we have lot of things to cover. We have lot of things to cover, my dear students. So I cannot wait for that long. So Christmas party begins now. Yes. Are you ready to enjoy the Christmas with me, with the celebration of the Christmas with revision of thermodynamics? Tell me everyone, are you ready? Yes. Hi Vamshi Sandras, very good evening. Hi Aram 10 Gaming, good evening. So are you ready to celebrate Christmas with me? Let's start the celebration. Because once I will start, it will be non-stop supersonic speed revision. because we have to cover a lot, my dear students. It's not possible to cover entire thermodynamics in 90 minutes, I'm telling you, but we will make it possible. We will make it possible together. Yes. So I think we should start the celebration, जिससे कि आप भी सेशन के बाद सेलिब्रेट कर सकें, and you should be feeling like today I have revised the thermodynamics subject. Now it's time, the real time for celebration of Christmas, right? तभी क्रिसमस मनाने में मजा आएगा जब आपका थर्मोडायनामिक्स कंप्लीट हो जाएगा. तो जब तक कंप्लीट नहीं होगा, until unless it's not completed, will not celebrate Christmas. Christmas will be celebrated after revision of thermodynamics. Okay, so let's begin. I will start with my introduction first. I am Vikas Sir. As you know, most of you already know my name. I have 5+ year teaching experience. I did my MTech in thermal engineering from Thapar University, and I have mentored more than 10,000+ aspirants for different exams like GATE, ESE, GATE. My area of expertise includes subjects of fluid mechanics, thermal and applied, and heat transfer subject. Okay, so let's begin the revision. Come on, everyone. Free full length mock test provide कर सकते हैं from grade up. Full length mock test will be provided to you. Don't worry, we will bring full length mock test also. Now this point we are going to start the revision. So only questions will be after the completion of revision. Okay. Now I'm going to start, and now I'm going to start like a supersonic missile. Mach number greater than 1. Just see that. So what is thermodynamics, my dear students? Thermodynamics, it is a branch of science. It is a science of energy interaction. Yes, it is a science of energy interaction. यही तो पढ़ते हैं आप लोग. It is a science of energy interaction and its effects on system and surrounding. Science of energy interaction and its effects on system and surrounding. Yes, two things are important here to highlight. One is science of energy interaction. And its effects on system and surrounding. So what is energy interaction here we are talking about? What kind of energy interaction we are talking about? The energy interaction will be in the form of mechanical and thermal energy. So energy interaction will be mainly in the form of two interactions. One is thermal energy in the form of heat. Thermal energy, because energy interaction may be of different types. Thermal energy and mechanical energy in the form of work. Okay, mechanical energy in the form of work and thermal energy in the form of heat. Okay, so this energy interaction will be studying in thermodynamics. And not only these two energy interaction, we'll be studying about some more. We'll be studying about the stored energy. We'll be studying about some stored energy like macroscopic and microscopic energies. What are these two types of energies? I will discuss with you these two types of energy. Or also macroscopic means kinetic and potential energies. Kinetic energy and potential energy, they comes under macroscopic energies. Okay, where bulk molecular behavior is studied. And microscopic means internal energy, where we study different types of energies like vibration energy, rotational energy, spin energy, transitional energy, nuclear energy. All this energy together comprise of internal energy. Okay, so these energy interaction we are going to study on system and surrounding, with respect to system and surrounding. So what is this system? क्या पहला part है thermo का? Yes, this is the first part and the only part of thermo we are going to revise. Okay, Vimal, who is the Sumant. Okay, now what is system, my dear students? What is system? Because we are not going to waste our time in definition and all, because we have to cover a lot of things, my dear, which are very important. System, what is system? It is a fixed region. It is a fixed region or space. यही तो definition होती है, fixed region or space where our study is focused. That is called system. Okay, that is called as system. Now this system can be of different types based on the energy and mass interaction. Based on energy and mass interaction, the system can be classified into three major types. It can be closed system, open system, and isolated system. Okay, now in the closed system there are no mass interaction. Mass interaction does not take place in closed system, as we call it closed, because it is control mass system. It is also called control mass system. Okay, because the mass inside the control volume, control mass will be constant in the closed system. Okay, yeah, exactly. System वही होता है जिस पे study करते हैं, definitely. And there will be energy interaction possible in the closed system, in the control mass system. There will be energy interaction possible in the form of heat, work, and other types of energy. For example, piston cylinder without walls. In your IC engine, we use piston cylinder arrangement, right? But in the piston cylinder arrangement also, during two process of compression and expansion, when compression and expansion take place, your inlet and exhaust valve do not operate. In that situation, it becomes a closed system. In the pressure cooker also, when the steam is not coming out from the pressure cooker, as long as steam is not coming out from pressure cooker, it remains as a closed system. Okay, so as long as mass interaction is not taking place, a system will be a closed system and only energy interaction will take place. In open system, both mass and energy interaction take place. Example, piston cylinder with valves. When the valves are operating, for example, during suction and exhaust, in the piston cylinder arrangement, the valves will be operating, the mass flow will take place. So in that situation, that will become an open system. Turbines, compressor, boiler, heat exchanger, pumps, and many of the devices operate as open system. Okay, and what is an isolated system? In which neither mass nor energy interaction take place. Neither there will be mass interaction, no energy interaction. Nothing will take place. Example is well insulated thermos containing hot coffee. That is an example of an example of a isolated system. You can keep your hot water, you can keep your hot coffee, you can keep your hot milk inside this thermos flask, okay, for many hours, depending on the type of the insulation. Yes, this is a cork which is providing the insulation inside the thermos flask, and because of that your water is able to remain hot for a long time. Okay. Example of different types of system can be understood with the help of this diagram. For example, you can see in the closed system only the energy interaction is taking place in the form of heat and work, but there is no mass interaction. So that is an closed system, no mass interaction. Okay. In the case of an open system, for example, boiler, in the boiler mass can flow as water and steam can come out from the boiler. In the turbine, mass can enter the turbine, superheated steam can enter the turbine, and exhaust steam can leave the turbine. Also, there is energy interaction in the form of heat and work in turbine, in boiler, as well as in pump and condenser. So these devices actually work as open system. So most of the devices work as open system. Alright, now this is isolated system example, thermos flask, where we'll be only studying about there will be no energy and mass interaction in the isolated system. Okay, so most of the devices work as open system. You can see that from here. Control volume system is closed system. No, my dear, open system comes under control volume. Control volume approach comes under control volume system is called as open system, because in the open system your volume is fixed, and in a fixed volume both mass and energy interaction will take place. That is called a control volume approach, that take place in the open system, while in the closed system we study the control mass approach. Okay, now we are going to study about the properties. What are the properties, my dear students? Properties, like every student, everyone who is present in the session, you must be having different types of properties. Some of you must be having some big hair, some of you must be having tall height, some of you must be having different types of complexion, right? So properties can be of different type. Property basically defines the characteristics of a system. Okay, characteristics of a system is called property. Now these characteristics can be defined with the help of two types of property, my dear students. One property is called as intensive or intrinsic property, another is called extensive or extrinsic properties. Okay, so everything has to be defined. Every system has a characteristic. For example, if I'm having two systems right now here, this system is having some pressure of let's say 1 kilopascal and temperature of let us say 20 degrees Celsius, and this is having the pressure of 10 kilopascal and temperature of let's say 50 degrees Celsius. So you can see that this system, let us say this is system 1 and this is system 2. So both the system are different from each other. Why? Because the properties of the system are different. Here the properties are different, here the properties are different. So what are these properties? They are characteristics of the system which characterize the system. Characterize का मतलब होता है बताना कि ये system different है from the other system. That is called characteristics of a system. Okay, so you can see system 1 is totally different from system 2 because pressure and temperature of system 1 and 2 are different. Okay, so intensive properties are those properties which are independent of the mass. ऐसी प्रॉपर्टीज जो मास से इंडिपेंडेंट होती हैं दे आर कॉल्ड इंटेंसिव प्रॉपर्टीज, दे आर मास इंडिपेंडेंट प्रॉपर्टीज. फॉर एग्जांपल प्रेशर, टेम्परेचर, विस्कोसिटी, थर्मल कंडक्टिविटी, डेंसिटी, they all called as intensive properties. They will not be affected by the change of mass. That is why they are called intensive properties. Next is extensive properties. They are called as mass dependent properties. Example, kinetic energy, internal energy, enthalpy and volume. They are called as extensive properties. Example, all the types of energy, kinetic energy, potential energy, internal energy, enthalpy, entropy, they all comes under volume, they all come under extensive properties. Most of the types of energies comes under the extensive properties. Okay, while if you divide an extensive property, any extensive property by mass, it is very obvious thing. If something is depending on the mass and you divide it by mass, it will become independent of mass and it will become intensive property. And if an extensive property have been converted into intensive property by dividing by mass, then this property will be called specific property. Okay, because this has been converted, it is a converted property from extensive property by dividing by mass. It was not intensive property. We have made it intensive property by dividing by mass. Okay, now it has become intensive property, and that is why it is called a specific property. So all these properties you are seeing right now here, if you divide it by mass, it will become specific kinetic energy, specific internal energy, specific entropy, specific enthalpy, specific volume. They all come under specific property, means intensive properties. Okay, so let me tell you some example of some intensive properties which you might remember. Okay, as intensive property: concentration, density, magnetic permeability, melting and boiling point, pressure, specific conductance, specific heat capacity. Yes, see, heat capacity is mass into specific heat. If you divide it by mass, it will become C, that is specific heat. Okay, so heat capacity is extensive property while specific heat is intensive property. Okay, specific internal energy, specific volume, surface tension, temperature, thermal conductivity, viscosity. You have to remember this table, and I will give you the PDF of this session. I will upload the PDF of this session in the in our Instagram channel. Okay, sorry, in our Telegram channel. Sorry, not Instagram. In Telegram channel, I don't use Instagram. In Telegram channel of our mechanical, so grade up ESE and GATE preparation channel. So in that I will share the PDF of this session. So you will get the PPT PDF of this whole session. So you don't need to worry, you don't need to write anything. You just understand it. Okay, you will get the entire PDF of this session. Okay, don't worry. This is the example of extensive properties. Amount of substance or mole. Number of mole come under the extensive property. Number of moles. Energy, enthalpy, entropy, Gibbs energy, heat capacity, Helmholtz energy, internal energy, mass and volume. They all come under the extensive property. So that is an example. And अगर आपने ये याद कर लिया, you don't need to worry about any question comes from any property, you can easily answer. Just remember this thing. Okay, so either you remember it from there that extensive property is mass dependent property, it depends on the mass, or you can remember this table. This is the example of maximum intensive property and extensive property given in this PPT. Okay, now let's come to another thing. Now we have understood about system and properties. Now you should understand what is the state of a system. For example, let us say this is one condition of a system. At this condition of system, we have pressure of, let us say we are having pressure of 1 bar and we are having volume of let's say 1 meter cube. Now at this point we are having the pressure, point 2, we are having pressure of 2 bar and we are having the volume of 3 meter cube. Now, what is the meaning of this thing? That means if you see this system at state 1, the state 1 condition as pressure is 1 bar and V1 is volume is 1 meter cube. And state 2 we are having pressure is 2 bar and volume is 3 meter cube. So this is the state. State means the condition of a system. Now if a system changes its condition, then it executes a process. That is called a process. If the condition of a system changes, it is called a process, and the path which is followed by the process is called a process path. So this is the path. So 1A2 will be called as process path and 1 to 2 is called a process. Now this process can be categorized as two types. One is quasi-static process and other is reversible process. We can totally divide it into two parts, quasi-static and reversible process. What is quasi-static? A process which occurs very, very slowly. Quasi means almost, and static means slow, very slow process. It is another name of quasi-static process, almost equilibrium. A process which is almost in equilibrium or which is almost very slow, that is called a quasi-static process. On a PV diagram, it is shown by joint line. Joint line means like this. A process which is non-quasi-static is called non-quasi-static process and shown by dotted line. Example, throttling process. Throttling process is non-quasi-static process, or we can also call it as irreversible process. Sir, quasi-static definition ठीक नहीं है. Definition ठीक नहीं है. Why it is not correct, Divyanshu? Please, can you please elaborate? Why you think that quasi-static process definition is not correct? हाँ, अच्छा, okay. You think like that. I hope you remember that quasi-static process is only meaning of quasi-static is a process which occurs very slowly. When you say it quasi-equilibrium, okay, then it means that a process which has taken place in such a way that the intermediate states of the process are in thermodynamic equilibrium. That means if a process has taken place such a very slowly and the intermediate states, these intermediate states are at thermodynamic equilibrium. That is called quasi-static process. So definition is exactly correct. Okay, I have only defined the quasi-static process. I have not defined the quasi-equilibrium thing. Okay, thermodynamic equilibrium. If the intermediate states are in thermodynamic equilibrium and a process occurring very slowly, then it will be called quasi-static or quasi-equilibrium process. Example is, suppose we are having a piston cylinder arrangement. We are having some weight kept on the piston. If the weight are suddenly removed, it will not be quasi-static. But if you remove the weight one by one, then you will be having a change of state from initial to final, following some equilibrium state. These are some equilibrium state. If you remove the weight one by one very slowly, you will be executing a quasi-static process. So the intermediate states will be at equilibrium and the process will occur very, very slowly. For example, the growth of your hair. Example is the growth of your hair, the growth of this plant, that comes under quasi-static. Okay, and if you talk about quasi-equilibrium, suppose we are having a cake. Today is Christmas, you will be eating a cake. Suppose we are having a cake. You have two options. You can eat the whole cake without cutting into different portions, or you can just divide this cake into different parts and you can make it cake pie and you can eat different portion of the cake. Or if you are using lift, that is not quasi-equilibrium. If you are using stairs, and you are climbing each and every stair by taking one step each, then it will be called quasi-equilibrium. Okay, so that is the difference between quasi-static and quasi-equilibrium. Both are different. Okay, now together we can say quasi-static and quasi-equilibrium. Together we can say that a process which has taken place very slowly and the intermediate states while executing a process are in thermodynamic equilibrium, that is called quasi-static process. But if quasi-static process are reversible process, let's see that. What is a reversible process? A process which has taken place in such a way from one point to another point. Suppose we are doing a process from A to B Let us say this is the forward path, and suppose we want to return back to our initial point. We want to return back, and we don't want to follow different path. We want to return it from the same path followed during the forward process. We want to reverse. We want to go back. Reverse path, and the reverse path is same as forward path. You are following the same path. Okay. In that situation, when you're returning back to the initial point for following the same path as you have taken in the forward direction, then that process will be called as reversible. But there should be no change in the surrounding condition. The condition is that there should be no change in the surrounding conditions. Okay, when you are executing a reversible process, the surrounding condition should not get affected by this reversible process. Okay, if a process is not reversible, it will be called irreversible process. For example, we are using the throttling process, throttling, free expansion. They all come under irreversible process. Okay, this is irreversible process. Now, one important thing, a reversible process you must be studying in thermodynamics so many times. For example, reversible adiabatic process, which is also called isentropic process. Now, a reversible process is the most efficient process. And it is very difficult to achieve in real condition. Okay, it is the ideal process also. A reversible process are quasi-static, but all quasi-static processes are not reversible. Yes, a reversible process can be called as quasi-static, but you cannot call a quasi-static process to be reversible. Only frictionless quasi-static process is reversible. Only frictionless quasi-static process is a reversible process. Okay, if a quasi-static process has taken place in such a way that there is no friction taking place during the process, then that quasi-static process will be called a reversible process. In your thermodynamic study, we generally assume that your quasi-static process is actually a frictionless process, and we generally take them both as same. But actually, quasi-static process can never be called as reversible until and unless there is no friction. If friction is not there, definitely a quasi-static process will be a reversible process. Okay. Example of reversible process are, there are very few reversible process, and one of the famous reversible process is isothermal process. Isothermal process is a reversible process which take place under phase change. A phase change process will be a reversible process. For example, change of phase from water to ice or from ice to water. That will be a reversible process. That can be possible. Okay. But if you see the example of an egg, if you want to make an omelette out of an egg, right? So it cannot be changed back into an egg. An omelette cannot be changed back into egg. That will be an irreversible process. That is an example, simple example. Okay. Now there are different other thermodynamic processes that I want to focus here. There are different other thermodynamic processes that we are going to study. One is isobaric process or isopistic process or constant pressure process. Okay, constant pressure process. Now this constant pressure process, a lot have been said about constant pressure process by Charles' law. According to Charles, for a given mass of a gas, at constant pressure, volume is directly proportional to temperature. That has been given by Charles' law. Okay, so Charles' law has actually defined about the constant pressure process, which is also called isobaric process, isopistic process. This constant pressure process you will be studying about in Brayton cycle, you will be studying about in Rankine cycle, in Diesel cycle. Okay, so this constant pressure process will be studying in many different cycles. Okay. Next is isochoric or isovolumetric or constant volume process. Okay, constant volume process, a process in which volume is kept constant. In solving some questions of thermodynamics, when you solve the questions, you will also come across a point which is called rigid closed system. When you will come across this word rigid means the volume is fixed. Okay, rigid means volume is fixed. They will sometimes not write that volume is constant, but it is constant volume, constant volume, or we can say that rigid system. If they will say rigid system, that means volume is constant. So my dear students, this have been given by Gay-Lussac. has given a law for constant volume process, that for constant volume for given mass of a gas, pressure is directly proportional to temperature. This has been given by Gay-Lussac law. Okay, so this is how we represent a constant volume process by a line parallel to pressure axis. Then we have isothermal process. This has been given by Boyle's law. Okay, so we have to be really very quick. Boyle's law. He said that for a given mass of gas at constant temperature, pressure is inversely proportional to volume, or PV is equal to constant. This equation is the equation of rectangular hyperbola, and that is why this process is also called as hyperbolic process. So maybe sometimes in your questions they will not write it as isothermal process. Sometimes they will write it as isothermal hyperbolic process. Okay, so always remember that hyperbolic process is same. You can call it as hyperbolic, or you can call it as isothermal process. Okay, next is adiabatic process. It is a process in which there is no heat transfer. No heat transfer takes place during adiabatic process. So generally, in order to make a process to be adiabatic, this process you are going to study many type cycles. Most of the cycles you will study adiabatic process, or to be very particular, we'll be studying about reversible adiabatic process. Okay, which is also called isentropic process. Okay, reversible adiabatic process or isentropic process you'll be studying in almost every cycle. Compression and expansion take place as reversible adiabatic. Okay, so this process is also very important. Polytropic process is defined by equation PV power n is equal to constant. Like adiabatic process defined by equation PV power gamma is equal to constant, where gamma is called as adiabatic index, and whose value is equal to Cp over Cv, specific heat at constant pressure by constant volume. Polytropic process is defined by equation PV power n is equal to constant, where n is called polytropic index, and for all the natural polytropic process, the value of n lies between 1 and gamma for all natural process. Generally, the value of n lies between minus infinity to infinity for general process, but for a process we study in thermodynamics as polytropic process, the value of n will lie between 1 and gamma, where 1 is the constant for example, in the isothermal process we represent PV is equal to constant. So here n is equal to 1 in isothermal process. In adiabatic it is gamma. Okay, so polytropic process will be lying between both of them. It will be PV power n is equal to constant. It will be lying between an isothermal and adiabatic process. Okay, clear everyone? Next, the slope of an isothermal adiabatic curve on PV diagram. On a pressure volume diagram, if you want to know the slope of isothermal adiabatic, so how can we know that? The slope of dP by dV for a isothermal process for constant temperature process equal to minus P by V, and for the slope of adiabatic process on a pressure volume diagram, adiabatic process, the slope on pressure volume diagram is equal to minus gamma of P by V. Okay, so you have to remember this also. It is also very important. That is, the slope of constant adiabatic process is gamma times of slope of constant temperature process on a PV diagram, pressure volume diagram. Next is representation of various process on the pressure volume diagram. Generally, for this representation, we can assume that the process is a very simple process given by equation PV power k is equal to constant, where k is any it can be expansion coefficient. Okay, it is a general process. Okay, and it is a general equation of an ideal gas. If the value of k becomes 0, it will be an isobaric process. If k is equal to 1, it will be isothermal. K is gamma, it will be adiabatic, and it is polytropic, and infinity, it will be isochoric process. Okay, so volume will become constant if value of k will become infinity. This question can come in an exam. If value of k becomes very large, infinite, then the process will become constant volume process. If the value of k becomes 1, it will become isothermal process. If k becomes 0, it will be isobaric process. Okay. Now, how can we represent different process on the pressure volume diagram? This is how you represent different process on the pressure volume diagram. This is constant pressure process. This is constant temperature process. This is polytropic, and this is adiabatic, and this is constant volume process. This is how we represent different type of process on a pressure volume diagram for compression. And for expansion, how do we represent expansion and compression process? Any process which goes from left to right, Any process which goes from left to right on a pressure volume diagram, that will be an expansion process. Okay, and any process which goes from right to left, then that process will be called as compression process. Okay, as you know that if the value of n increases, the work input required for compression will increase. If the value of n or value of this power k increases, as you go in this direction, the work input will be increasing. The least work input is required in compression in isothermal process and maximum work input in the adiabatic process. Similarly, the maximum work output in expansion process will be getting in constant pressure process. In constant pressure process, the work output will be maximum for expansion and it will be least for adiabatic process. Okay, so that is a very important thing, that work output is directly proportional to n. If value of n will increase, sorry, it is not directly, it is inversely proportional to n. Okay, अगर n की value बढ़ती है, if value of n will increase, then work output will decrease. Inversely proportional to n. अगर n की value बढ़ेगी, then work output or expansion work will decrease, and work input is directly proportional to value of n. Telegram channel name. Okay, I'm just going to write the name of Telegram channel. Wait 1 second. Yes, the name of the Telegram channel is Grade Up. It is Grade Up, ESE and GATE. You can join me on the Telegram channel also. GATE/ME and इसके आगे होगा preparation. Okay, that is the name of the Telegram channel. Okay, I will write it in the end also. I will write the name of the channel. Okay, don't worry. Clear? So let's move on further. This is the name of our Telegram channel. You can join here, and to get the updates of the upcoming session and to get the PDF of the session, you can join our Telegram channel also. Now let's come to ideal gas equation. It is very important. Ideal gas equation. Generally the gases are real. Real means they do not follow the ideal gas equation. For example, in the fluid mechanics, you study real fluids and ideal fluids. Ideal fluid follow some assumptions like they will be having zero viscosity, zero surface tension, they are incompressible. In the same manner, a gas will be called as an ideal gas if it follows some assumptions. And these assumptions are: intermolecular force of attraction between the gas molecules should be totally negligible, and molecular volume should be negligible as compared to the container volume in which the molecules have been kept. For example, these are the gas molecules. So the molecules of the volume of the gas molecule should be so small that it is almost negligible as compared to the container in which the gases have been kept. Okay, now there are two conditions which are favorable for a gas to be considered as an ideal gas. This is very important. These favorable conditions are low pressure and high temperature. If a gas has low pressure and high temperature, then it will be called as an ideal gas. Okay, ideal gas equation is given by PV is equal to mRT. This is the ideal gas equation where PV is equal to mRT, where P is called as absolute pressure. What is this absolute pressure? In thermodynamics study, in fluid mechanics also you have studied about absolute pressure. Absolute pressure is equal to sum of atmospheric pressure plus gauge pressure. Gauge pressure is the pressure that you get from some mechanical instrument, and that is atmospheric pressure. Its value is fixed. Okay. So this is absolute pressure. It is always positive. Its value is always positive. That is why we keep here absolute pressure. V is the volume, M is the mass, R is the characteristic gas constant. This is characteristic gas constant, and T is the absolute temperature. It has to be kept in Kelvin, absolute temperature, and that has to be kept in Kelvin. Okay, clear everyone? Clear? So this is very important that in this ideal gas equation, one thing is very important, that the pressure in the ideal gas equation has to be absolute pressure. This is very important. Now this gas constant R, it is equal to universal gas constant divided by molecular mass. Okay. Now, my dear students, this universal gas constant has a value of 8.314 kilojoule, and the unit is kilojoule per kilomole Kelvin or joule per mole Kelvin. and m is the molecular weight, and molar weight, we can say molar mass, that is equal to, it is molar mass, and its value is equal to, its unit is kilogram per mole. Okay, so the unit of gas constant is equal to kilojoule per kg Kelvin. Okay, superheated steam is approximately, superheated vapor can be approximately treated as ideal gas. But I will tell you about this thing in properties of pure substance topic. They can be treated as an ideal gas. Only superheated vapor can be treated as an ideal gas, and you can apply the ideal gas equation in the superheated region of a phase change diagram. Okay, now this is gas constant. Gas constant depends on universal gas constant. This is universal gas constant whose value is constant. So the gas constant depends on the molar mass, inversely proportional to the molar mass. And for example, for oxygen, the molar mass will be equal to 32. For carbon dioxide, that will be 44, and for sulfur dioxide will be 64. Okay, 64. Okay, so likewise you can see that the molar mass of different gases is different. For nitrogen it is 28. Okay, so molar mass is different for different gases. So gas constant depends on the molar mass, inversely proportional to the molar mass. That is a very important thing, that it is inversely proportional to the molar mass. Okay, that is a very important relation. Now, as I told you that PV is equal to MRT and R is equal to universal gas constant by molar mass. That you can also write it as M by M into R universal into T. This mass by molar mass is equal to number of moles. Okay, this is also ideal gas equation. PV is equal to N into universal gas constant into T. Okay, this is universal gas constant. This is the number of moles of the gas. Okay, this is also one form of ideal gas equation that you can use in solving some questions. Okay, now behavior of the real gases, like real gases deviate from the ideal gas behavior. I will tell you about that also. How does they deviate from ideal gas? But a real gas will behave as an ideal gas at low pressure and high temperature. At low pressure and high temperature, a gas will behave exactly like a perfect or ideal gas. Although perfect and ideal gas both are different in some aspect, but a real gas behave as an ideal gas at high temperature and low pressure. This is very important thing. Okay, if the temperature is decreased or pressure is increased, the behavior of a gas is very different from the behavior of a perfect gas. At high pressure, real gas does not behave as a perfect gas or ideal gas. Okay, now we are going to study the ideal gas equation for various processes. This is very important slide. Try to remember this thing. Okay, although you will get a PDF of this, but this table is very important. Ideal gas equation for various processes. For example, for isobaric process, constant pressure process, as pressure is constant, let us say that we are having a system which is changing state from 1 to 2. Okay, a state is, or we can say system is changing state from 1 to 2 for different process. It can be isobaric process, can be isothermal process, it can be isochoric process. So my dear students, for isobaric process, volume is directly proportional to temperature. So if a system is changing state from 1 to 2, you can write this equation as, yes, I think there is some delay in the, yes. Okay, so for isochoric process, the equation, this is the ideal gas equation. For isothermal, this is the ideal gas equation, as PV is equal to constant is the equation of an isothermal process. So if the system is changing state, so you can write it as P1 by P2 is equal to V2 by V1. So this is the ideal gas equation for isothermal process. For adiabatic process, this is most important equation, most important equation. Mark it. This equation you will be using in many of this thing. Okay, so my dear student, this equation will be using in solving the questions of Otto cycle, diesel cycle, Rankine cycle, Brayton cycle. In many of these, you will be using this equation for adiabatic process. P1 V1 power gamma is equal to V2 V2 power gamma. Okay, so like in the case of Otto cycle, you will be getting from here that P2 by P1 will be equal to V1 by V2 over gamma. So this you will be getting in Otto cycle. It is very important equation. Similarly, this equation is also very important. T2 by T1 is equal to P2 by P1 power gamma S 1 by gamma. This is also quite important in Brayton cycle. This equation also very important. That is T2 by T1 is equal to V1 by V2 over gamma minus 1. Okay, so these equations are very important for adiabatic process, and for polytropic process the equation is almost same. Only difference is that you have to replace the gamma. The gamma will be replaced by n. This is the only difference between polytropic and adiabatic process. Otherwise the equation for polytropic and adiabatic process is almost same. Video is not clear. It looks like blur image. Upon Raj, I think video is clear. If it is not looking clear, my dear, so it might be possible that your there is some issue of the internet. Please tell me, is video clear? Are this equation clear or not? Please tell me, everyone. Yes? Are this equation clear or not? Or otherwise I will write this equation again. If this equation are not clear, I will write it again. Yes, everyone, tell me quickly. Hurry up guys, please tell me. Are this equation clear, my dear students? Upon Raj, please reload the session. It might be there, it might be possible that there is some internet issue, and because of that it might be possible that the video quality is not clear. मैं दिख नहीं रहा हूं, मैंने अपने आप को भी छुपा रखा है. I have hidden myself, इसलिए नहीं दिख रहा हूं. Okay. Now let's come to another important aspect of closed system. In the closed system, we study about non-flow work or boundary work. Non-flow work or boundary work you study in the closed system. This is the work which we obtain in a closed system, that is called non-flow work or boundary work. Okay. Okay, no problem, Appan Raj, no problem. If the video quality is not clear, you can reload the session. Okay, my dear. So non-flow work or the boundary work or the closed system work is given by integral of PdV. This is very, very important. Remember that. For applying this formula, you have to use this closed system, quasi-static, or we can say, to be very particular, quasi-static or frictionless quasi-static, or boundary or non-flow. Non-flow means closed system where the mass cannot flow. Why it is called non-flow? Non-flow means the mass cannot flow in and out. Mass cannot flow, and that happens in the case of closed system. Non-flow process take place in the closed system. Okay. For any process going from left to right on the PV diagram, work is done by system and considered positive. Now again I am going to hide myself. If a process is taking place on a PV diagram, the area under the PV diagram for a reversible process, area under PV diagram gives work done. Okay, if any process is going from left to right, then the work will be positive, and that will be called expansion work. And if any process going from right to left, then the work will be negative, and that will be called as compression work. So compression work is always negative work. For example, in the case of compression, the work is negative because compression work is negative because work is given to the system. It is negative, and work is positive in the case of turbine because it is expansion work. Okay. Now another thing is open system work. Open system work is represented by this. This is how you represent the open system work. On a pressure volume diagram, it is represented by plotting. If you are basically obtaining the work on the pressure axis, by plotting the curve on the pressure axis, it will give you the open system work, which will be equal to minus VdP work. This is called open system work. Okay. Now, my dear students, this is the open system work formula. For an adiabatic process, the open system work is equal to gamma times of closed system work. This is very, very important. For polytropic process, open system work is equal to n times of closed system work. And for isothermal process, open system work is equal to closed system work. They both becomes equal. So this is a very, very important relation, and please remember this thing. It is very, very important. There are some important points related to non-flow work. It is a path function. For example, if you are intended to find a work, non-flow work for different paths. For example, the path 1A2, the work under path 1A2 will not be equal to work under path 1B2. Both work will be different. That means although the initial and final points are same, but the work obtained between these 2 points, that is not same. So work obtained is not same between the two between same points, but between different paths, because the path here are different. Okay, that is why work is a path function. It is not a point function or state function. All the properties are point function or state function. All the properties are point function or state function. This is very, very important point. Okay, जितनी भी आपकी properties होती हैं, they are point function or state function. Why negative? My dear students, compression work is negative because work is done on the system. When you do work on the system, you are giving work as input. Okay, generally when you obtain work as output from the system, we call it as positive work. For example, in case of turbine. In case of compressor, you have to give work as input with the help of a motor. So you are actually spending your electrical energy to operate a compressor and pump. That is why we call compression work as negative work, because you are giving work to the system. Okay, Vikas? But in the case of turbine, you are obtaining the mechanical work out of turbine, and by that mechanical work, you are operating a generator and getting electrical energy. That is why turbine work is called positive work, while compression work is called negative work. Okay? Because you are spending your electrical energy, you are spending your money to obtain compression work. Okay? So that is why it is taken as negative. In case of turbine, you are getting work as output. Okay? Oh, work is not a... See, Appan Raj, we have not yet reached the topic of maximum work. Maximum work पे अभी हम नहीं आए हैं. Maximum work पे अभी हम आएंगे. We don't worry. I will come to maximum work topic. There I will explain. Vikas Yadav, is your question clear? Why the work is negative? Now it is inexact differential. That means if you integrate this work from 1 to 2, it is not equal to W2 minus W1. While if you integrate any property from 1 to 2, it will be equal to H2 minus H1. This is the meaning of that properties. All properties are exact differential. Exact differential mean, this is the meaning of exact differential in mathematics. Okay. While in the case, this is the property of inexact differential. This is the property of inexact differential. And this is the property of exact differential. All the properties like pressure, temperature, they all come under as state function. They are all comes under state function or point function, and they also come under exact differential. While heat and work, they are called as both are called as inexact differential and path function. Okay, path function means that their value depends on the path. It does not depend on the initial and final points. Agar point पे depend करती, then definitely the work of W12 had been equal to W1V2. But it is not equal because it is not depends on the points. It is depending on the path. Okay. It is a boundary phenomena. Yes, you can see that non-flow work is a boundary work. You know that it is a transient phenomena. Transient means something which changes with time. Yes, it is when the boundary of the system changes, then work is obtained. So because when the boundary changes with time and then this work is obtained, that is why it is a transient phenomena. It is not a property or point function. Yes, it is not a property. Is heat is exact differential? No, my dear. Heat and work both are inexact differential and both are path function. Heat and work both are inexact differential and path function, while all the properties are point function and exact differential. Okay, let's move on to another topic quickly. Now we are going to study the non-transient means. What is the meaning of transient? Transient नहीं पता बेटा, आपने स्टेडी अनस्टेडी हीट ट्रांसफर तो पढ़ ही लिया होगा. हीट ट्रांसफर में Transient means which is unsteady, which is changing with time, something which changes with time. जो time के साथ change हो, that is called transient. That is called transient, something which changes with time. Okay, clear everyone? How Q minus W is path independent? I will tell you, don't worry. Just have patience, Shivam. Okay, don't worry. Now we are going to study the non-flow work in various processes in isochoric, isometric. Non-flow work means this work, PdV work. Now PdV work in isochoric or constant volume process where volume is constant. If volume is constant, then work is equal to integral of PdV. The change in volume will be 0. So this work will also be 0. Non-flow work will be 0 for constant volume process. Okay. Who told you, Imran Khan, that we can write heat as Q2 minus Q1? We cannot write heat as Q2 minus Q1. Have you seen anywhere in thermodynamics where I have written heat as Q2 minus Q1? Anywhere heat is written Q2 minus Q1? Or change in heat is equal to Q2 minus Q1? Have I written anywhere like that? Anywhere you have seen in thermodynamics, any book of thermodynamics, Imran Khan, have you seen that change in heat is written as Q2 minus Q1? Yes. See, there is a difference between heat and heat transfer. Heat and heat transfer में different होता है. Okay. Heat transfer and heat is different. Heat is just a thermal energy and transfer of heat depends on the temperature. Okay. So heat cannot be written as like that. Isobaric or isobaric process, the work is equal to P of V2 minus V1. This is how you find the work. It is MR of T2 minus T1, non-flow work. Isothermal process, the work is equal to P1 V1 log of V2 by V1 or P1 V1 log of P1 by P2. Adiabatic process, the work is equal to P1 V1 minus P2 V2 over gamma minus 1, or it is equal to MR of T1 minus T2 over gamma minus 1. Okay, yes. Next is polytropic process. Oh, that is, see, when you are applying the first law of thermodynamics, second law of thermodynamics, that is first law of thermodynamics for a cycle. That is first law of thermodynamics for a cycle, that net heat is equal to net work. That you can definitely apply for a cycle, but for a process you cannot write it like that. Okay. For a polytropic process, the work is equal to P1 V1 minus P2 V2 over N minus 1. It is equal to MR of T1 minus T2 over N minus 1. Okay, so that is how you have to remember the non-flow work formula for different process. Next is thermodynamic equilibrium. A system will be called as thermodynamic equilibrium if it follows. See, solution कैसे निकलता है रघुनाथ? Here I am not going to explain how. देखिए, I can explain you how to get the solution, but it is a revision session. I have to cover a lot of things. I cannot teach you how to derive the formula. Okay, there is no time for that. Okay. In some other session, I can definitely derive that, but right now we don't have time, my dear. Okay, system is said to be in thermodynamic equilibrium if it follows these type of equilibrium: thermal, mechanical, and chemical equilibrium, and also sometimes phase equilibrium if अगर mention है आपके exam में. Okay, thermal equilibrium means equality of temperature. It is also called equality of temperature. If the temperature is same everywhere in the system, that is called thermal equilibrium. And zeroth law of thermodynamics is based on thermal equilibrium. Mechanical equilibrium means equality of forces. Chemical equilibrium means equality of chemical potential. And phase equilibrium means the mass of phase is constant with time. Okay. Generally, this is not given, my dear, in the question, in the exam. But yes, these three equilibrium. If thermal, mechanical, and chemical equilibrium are satisfied, then the system is called in thermodynamic equilibrium. Okay. But zeroth law of thermodynamics is based only on thermal equilibrium. It is not based on thermodynamic, only on thermal equilibrium. Okay, that is equality of temperature. It is on that. It is only on the thermal equilibrium on which zeroth law of thermodynamics is based upon. Okay. So if there are three different bodies, body A, body B, and body C. If body A is in thermal equilibrium with body C and body B is in thermal equilibrium with body C, then body A will also be in thermal equilibrium with body B. Here the third body acts as thermometer. Here this body will act as thermometer. For example, when you measure the temperature of your body, you use a thermometer, you put that thermometer inside your mouth or inside your armpit, and due to thermal equilibrium, you are able to get the temperature of your body in that thermometer. Okay, so there are different types of thermometer. And how do we measure the temperature from thermometer? From zeroth law of thermodynamics. Zeroth law of thermodynamics. The zeroth law of thermodynamics defines two things. It defines temperature. It defines temperature, and it also gave thermometer. So thermometers based on the zeroth law of thermodynamics. There are different types of thermometer. The thermometer that you use in your house, that is called liquid in bulb thermometer. Okay, in that thermometric property is actually the expansion of the or the rise of the liquid inside the thermometer. That is the thermometric property. The length of the rise of the liquid in thermometer, that is thermometric property. But there are different types of thermometer, and all these thermometers are based on different types of thermometric property. For example, in resistance thermometer, which is based on Wheatstone bridge, resistance thermometer, the resistance is the thermometric property. Resistance is thermometric property. They are based on Wheatstone bridge principle. And by measuring the resistance, and by converting into different this equation. Okay, so by finding the value of the resistance, we can find the value of temperature by this resistance thermometer. Similarly, we have the thermocouple. Thermocouple is also a thermometer which is based on Seebeck effect. Seebeck effect. If two different types of materials are joined together to make two junctions of a thermometer, of a thermocouple, and if voltage start to flow between these two junctions, then an EMF will be produced, electromagnetic force. That EMF will be proportional to the temperature difference. By measuring one of the temperature, you can find the other temperature, and by getting the value of EMF. This is how the thermocouple are based. Thermocouple are based on this thermometric property which is called EMF or electromotive force. Its unit is in volt. Then we have constant pressure gas thermometer. Constant pressure gas thermometer. Here the thermometric property will be volume. Volume will be directly proportional to temperature. Volume will be the thermometric property. And constant volume gas thermometer. Constant volume gas thermometer. In here the pressure will be directly proportional to temperature. So pressure will be thermometric property in the case of constant volume gas thermometer. So there are different types of thermometer, and in these thermometer, by measuring the value of EMF, resistance, volume, pressure, you can get the value of temperature. Now there are different types of temperature scale, but primary important one are Celsius, Fahrenheit and Kelvin scale. These scales are very, very important. So generally in the exam, they can give you the value of temperature in degree Celsius. They can ask you to find temperature in degree Fahrenheit. Okay, and vice versa also. So this is the conversion formula. You have to remember that temperature in degree Celsius minus the ice point is divided by steam point minus ice point is equal to temperature in degree Fahrenheit minus ice point. That is, the ice point in degree Fahrenheit is 32 degree Fahrenheit, and this is steam point in degree Fahrenheit is 212 degree Fahrenheit. So okay, so by using this formula you can convert that degree Fahrenheit into degree Celsius or Celsius degree Fahrenheit. Okay, so my dear students, how the question comes in your GATE exam. The question comes that there is a new scale. A new scale have been given by some scientist. Let us say that new scale is degree N. Okay, and they will give you that for this new scale the temperature of ice point is 100 degree N and steam point is 400 degree N. Now they will ask you to find the value of temperature in new scale in terms of degree Celsius. At let us say they will say at 50 degrees Celsius find degree N. So how you will use this formula, it will be 50 minus 0 divided by 100 minus 0 is equal to degree N minus 100 divided by 400 minus 100. So from here you can use this formula, and by using this formula you can simply find the value of this new temperature scale. Okay, using this relation, how to develop new temperature scale. This is how you develop the new temperature scale. Okay, so if they will give you any new temperature scale, let us say they have given degree X scale. So you can, and they ask you to find the temperature at 60 degrees Celsius. That will be 60 minus 100 divided by 100 minus 0 is equal to degree X minus 100 divided by 400 minus 300. So let us say they have given a new temperature scale which is degree X. The ice point is 400 degrees, sorry, steam point is 400 degree X and ice point is 100 degree X. So you can use this relation to find the value of the new scale. Okay, temperature in the new scale. Clear everyone? Yes, this is the very important thing that can be asked in the GATE exam. They can ask you these type of questions. Now let's move to first law of thermodynamics. First law of thermodynamics is also called law of conservation of energy. That is, energy can neither be created nor be destroyed. It can only be transformed from one form to another. It talks about the law of conservation of energy. Let us say there are different types of energy acting on the system. Okay, so these are the energy 1, 2, 3, 4. They are coming into the system and these energy are going out of system. So according to energy conservation principle, the energy total coming in is equal to energy going out. So this is the energy conservation principle which is based on first law of thermodynamics. But when we study first law of thermodynamics, we study different types of energy. The different types of energies are basically mechanical energy, thermal energy, internal energy, potential energy, kinetic energy, chemical energy, and etc. Okay, so there are different types of energy. Mechanical energy means work, thermal energy means heat. Internal energy you will study this energy, internal energy, which is also called microscopic form of energy. It contains different types of energy. Microscopic and macroscopic are two different approach of thermodynamics. In macroscopic approach, we study the average molecular behavior. And in microscopic approach, we study the individual molecular behavior, the behavior of individual each and every molecule. That is called microscopic approach. Okay, so in microscopic approach, we generally study the internal energy. In macroscopic, we study potential and kinetic energy. Okay, that is all different types of energy. Now, according to first law of thermodynamics for closed system in a cycle. In a cycle, what is a cycle? I forgot to tell you that if a system changes state from 1 to 2 through some path, let us say this is the path, and if the system returns back to the initial point, not following the same path but a different path is followed and system returns back to the initial point, this is point 1, then that is called as a cycle. That is called a cycle or thermodynamic cycle. Now for this thermodynamic cycle, the law which have been given by first law of thermodynamics, which have been given by Joule, actually Joule has given this first law of thermodynamics, and according to Joule, for a closed system in a cycle, the net heat transfer is equal to net work transfer, and this is the very important one. Okay, so net heat is equal to net work. Net heat transfer is equal to net work. But this is applicable only for a cycle. In process, you will get to see that in isothermal process, the heat is equal to work. You will study that. But that is only an exception, that in isothermal process, heat is equal to work. But for this cycle, for a closed system in a cycle, which is, it can be reversible cycle, it can be irreversible cycle. What is a reversible and irreversible cycle? Suppose we are having a cycle which is formed by only two reversible processes. Only reversible processes are there in the cycle, reversible process. If a cycle have been formed by reversible process, then it will be called reversible cycle. And if there is a cycle which is formed by one reversible and one irreversible process, let us say there is a cycle which has been formed by this one reversible process and another is irreversible process, then this cycle will be called as irreversible cycle. But whether it is reversible cycle or irreversible cycle, doesn't matter. This first law of thermodynamics for a cycle will be followed for both reversible and irreversible cycle. And this law you must have used in almost every cycle, whether it is Rankine cycle, Brayton cycle, diesel cycle. In almost every cycle you use this first law of thermodynamics, that is net work is equal to net heat. You use this now, heat supplied minus heat rejected. So you use this for a cycle. Net heat is equal to net work. Okay, so you can use this for a cycle. For a cycle only you can use this. Now, from first law of thermodynamics, you have got a very important conclusion that Q minus W is equal to change in energy. I'm not going to derive this relation, but one of the student was asking, sir, how Q minus W is equal to a change in property? Because this we have got from derivation of first law of thermodynamics. This is what we have got from first law of thermodynamics. That is change in heat minus the heat given to the system and work done by system is equal to change in energy, and that energy is change in any property. That property is called as energy. It has been defined by first law of thermodynamics. This has been given for first law of thermodynamics. So this is first law of thermodynamics for a process. First law of thermodynamics for process in closed system. Now this is the final relation you get, and this Q minus W, will be called as point function. Why? It is equal to point function because Q minus W you are getting as change in energy. Why? Energy is a point function. It is a point function. That is why Q minus W will be taken as point function. But Q and W individually they are path function. Individually they are path function, but difference of Q minus W will be taken as point function. Okay, this is very important thing. Hi Kuldeep Datta, very good evening my dear student, my dear Kuldeep. Well, good evening to the session. So Q minus W is a point function. This is energy. Now this energy can be sum of kinetic energy plus potential energy plus internal energy U. So if we find change in energy, that will be written as change in kinetic energy plus change in potential energy plus change in internal energy. If these two energies are negligible, then change in energy will be equal to change in internal energy. And you can write first law of thermodynamics as del Q minus del W is equal to du. Okay, this is the first law of thermodynamics. If you neglect the kinetic and potential energy, this is what first law of thermodynamics for a closed system in a process you get. And sometimes you also write that for a closed system, if you are using closed system and if it is a quasi-static process, then work can also be written as PdV work for a closed system. Then this also you get as du plus PdV. Okay. So for that you apply the assumption that change in kinetic energy and potential energy is negligible, and change in kinetic energy and potential energy is negligible, and also it is a closed system and quasi-static. In that condition you will be getting this equation for first law of thermodynamics for a process. Otherwise you will be getting this equation. Okay. Now my dear students, a very important thing, heat transfer is also a path function like work transfer. It is also not a property. It is not a property or point function. It is an inexact differential. It is a transient phenomena. It is a boundary phenomena. These are important points regarding heat transfer. One more important thing are sign conventions. We'll be using some sign convention in the first law of thermodynamics, and these sign conventions are very, very important, my dear students. Let us say we are having a system. And if some heat is entering into the system and some heat is leaving the system, if some work is done on the system and if some work is done by the system, then work done on the system is equal to negative work. Heat entering into the system is positive. Heat leaving the system will be taken as negative, and work done by system will be taken as positive. For example, turbine work. Turbine work is work done by system. It is positive. For example, compressor work done on the system is negative. For example, heat given to the system, example boiler, it is positive. And for example, heat rejected, example condenser. Okay, so when a heat is entering into the system, it will be taken as positive. These sign conventions are very, very important for solving the numericals of first law of thermodynamics for a closed system. Without this sign convention, you will end up in getting some wrong results. So these sign conventions are very, very important. Okay, remember that. What is transient? Other thing I have just explained, transient. Transient means something which changes with time. Transient heat conduction आपने पढ़ा होगा, unsteady heat transfer. Heat transfer subject में आपने पढ़ा होगा. You must have studied this in heat transfer subject. Unsteady heat transfer or transient heat transfer. पढ़ा है ना? Transient means something which changes with time. Okay. Now from first law of thermodynamics you get one more thing. Energy of an isolated system is constant. Okay. Energy of an isolated system is constant. This is also a very important result you get from first law of thermodynamics. My dear students, I know you are having some queries, but suppose just think about that. Right now I am only on first law of thermodynamics. We have to revise a lot of things. So if continuously will be having some queries, don't worry. At the end of the lecture, I will explain everything. Okay, but please give me some time. Clear? Clockwise cycle DS diagram is engine. Arun, as I have just explained on the pressure volume diagram, if some work is done from right to left, it is negative work. Yeah, there are sign convention. If the work is done from left to right, it is positive work on a PV diagram. There are sign convention on the pressure column diagram also, like in the heat transfer. Let's talk about something else. This is an important thing. You are having your different questions. I can understand that, but right now our target is different, my dear student. Right now our target is to understand this conclusion of first law of thermodynamics. Energy of an isolated system. What is the isolated system? No energy and mass interaction. That means if it is an isolated system, heat transfer, energy transfer, these all will be zero. So if this is zero, then energy will be constant. So energy of an isolated system or universe is constant. This has been given by first law of thermodynamics. Perpetual motion machine. It is a hypothetical machine which is also called PMM1. Example of hypothetical machine is a bike without petrol. Bike without petrol is an example of, or if you are going to ATM and you are not having any cash in your account, how can you get money from that, right? So bike without petrol cannot run. Similarly, you cannot get money out of your ATM if you are not having any bank balance in your account, right? So perpetual machine of first kind is basically a hypothetical machine which violates first law of thermodynamics. It gives you work continuously without any energy input. No energy input, but you are getting output energy. It is not possible. You cannot extract work from something. If Sai Kiran Reddy, my dear, linear cycle we are not going to understand here. This is a revision of thermodynamics, my dear Sai Kiran. In IC engine, I will explain linear cycle. It is thermodynamics. Thermodynamics में linear cycle कहाँ से आ गया? 8th standard cycle पढ़ेंगे IC engine में. There we study about the linear cycle. Okay. But try to calm down your questions, my dear. You are having many questions, I can understand that. But these questions will be answered based on the subject. This is a subject of thermodynamics. If you are going to ask questions of IC engine, how I am going to explain that? Okay. Now let's talk about the heat. Heat is what? Heat is the energy transferred to or from thermodynamic system due to difference in temperature. See, heat is of two types. Sensible heat. It is due to temperature difference, and the other is latent heat. The heat required for phase transfer is called latent heat, and the heat which flows due to temperature difference is called as sensible heat, and the heat which flows due to phase change, which is required during phase change, is called latent heat. Okay, so these are the two different types of heat in which the heat has been characterized. According to calorimetry, this heat transfer is directly proportional to mass, directly proportional to temperature difference, and you get this constant which is called specific heat. Now this specific heat, see, it is single. There is single value of specific heat for liquid and gas, solid. For liquid and solid, the specific heat is single. Okay, but for the gases, the specific heat is different. It is of two types. The specific heat of gases is divided into two types: Cp and Cv, specific heat at constant pressure and specific heat at constant volume. Okay, so what is Cp? It is the amount of heat required to raise the temperature of unit mass of gas through 1 degree Celsius when heated at constant pressure, and similarly specific heat at constant volume. Now there are some important relation between specific heat, and the first relation is that Cp is always greater than Cv, because if you are heating a system, a constant pressure system, which is at constant pressure, if you are applying some heat here, then that heat will be used for two things. It will be used for increase of internal energy and also for doing some work. So that heat will at constant pressure, it goes into doing some work and also for increasing the internal energy. But at constant volume, if you are applying heat to a system at constant volume, the volume is constant. If it is a rigid system, then work will be zero. So the heat transfer at constant volume is only equal to change in internal energy. Obviously, when you are supplying heat at constant volume, then you are only increasing the internal energy. But when you are supplying the heat at constant pressure, not only internal energy increase, but some external work is also done. So here you require more heat. More heat is to be given at constant pressure as compared to constant volume, because heat at constant pressure is more than constant volume, and that is why Cp is greater than Cv. Okay, so why Cp is greater than Cv? The only reason is that, my dear students, because at constant pressure, if you heat a system, then that heat goes into not only doing some external work but also increasing the internal energy. When you heat a system at constant volume, because at constant volume no work is obtained, work is 0. So all the heat goes into increasing the internal energy. Okay. So here we require less heat. At constant volume we require less heat as compared to at constant pressure. So that is why heat at constant pressure is more than heat at constant volume, and that is why Cp is greater than Cv. Okay. The difference of Cp minus Cv is equal to R. This is the Mayer's equation. This is a Mayer's equation that Cp minus Cv is equal to R, because Cp is always greater than Cv, and the difference of these two quantities will be equal to the gas constant, and the ratio of Cp by Cv is equal to adiabatic index. Now this adiabatic index is different for different types of gases. For monatomic gases like hydrogen and helium, the value of Cp is equal to, for monatomic gases like helium and argon, helium and argon, the value of gamma is equal to 1.67. For diatomic gases like oxygen and nitrogen, and generally for ideal gas also, the value of gamma is equal to 1.4. And for polyatomic gases like carbon dioxide, the value of gamma is 1.33. Cp, Cv and gamma for monatomic gases remains constant with temperature. So for monatomic gases, the value of Cp, Cv and gamma value remains constant most of the time. Okay. Now there is very important relation for heat interaction various process. What is the heat interaction various process? Enthalpy. Before we study the heat interaction for different process, we have to understand one very important thing, which is enthalpy. Enthalpy is the total heat content of the system. The total heat content is called enthalpy, which is equal to sum of internal energy plus flow work. Okay, flow work. What is the flow work? It is the work required in the open system for maintaining a continuous flow through control volume. Let us say we are having a control volume system. In the control volume system, although the volume is fixed, for the fixed volume, some mass will be entering the system and some mass will be leaving the system. So the work which is required for pushing this mass into the control volume and pushing the mass out of the control volume, that work is called as flow work. Okay, this work is required for flow work, or flow energy is the energy which is required in the open system for pushing the mass into the control volume and leaving the control volume. Okay, so this is the enthalpy. It is the sum of U plus PV. Now let us understand the heat interaction is various process. For a constant volume process, as you have understood that for a constant volume process, the work is 0, right? So if there is no work in the constant volume process, so heat transfer will be equal to change in internal energy only, which is equal to mCv dt. For constant pressure process, the heat transfer at constant pressure process is equal to change in enthalpy only. This is the Mayer's relation. It is very, very important. One is Mayer relation and one is this, gamma is equal to Cp by Cv. By combining these two equations, we'll be getting these two important results, that Cp is equal to gamma into R over gamma minus 1 and Cv is equal to R over gamma minus 1. These two relations are very, very important. These are very, very important relations. You will be using these two relations in solving many of the numericals in thermodynamics. Okay. Gamma value depends on the type of gas. I have just told you monatomic gases gamma is 1.67, and for gas with n degree freedom, our gas with n degree of freedom क्या होती है? These are the number of independent intensive variables used to define the state of a system. So gamma value is equal to 1 plus 2 by n for n degree of freedom. For a system with n degree of freedom, the value of gamma is equal to 1 plus 2 by n. But directly you can remember this, that gamma is equal to 1.67 for monatomic gases like helium and argon. For diatomic gases like oxygen and nitrogen, it is equal to 1.4. Okay. And generally, if nothing is mentioned, you have to take gases are generally diatomic. Like gases are generally diatomic, so you have to take gamma as 1.4, and for polyatomic it is 1.33. Okay. Now I have told you heat interaction for constant pressure process equal to change in enthalpy. It is equal to mCp dt. And for constant volume process, it is equal to change in internal energy. It is equal to mCv dt. What about constant temperature process? For constant temperature process, du will be 0. Why? Because du is equal to mCv dt. At constant temperature, du will be 0. So heat transfer at constant temperature process is equal to work. So for an isothermal process, heat interaction is equal to work interaction. Okay, I have already told about the quasi-static process, G. Srinu. You can watch the lecture again, my dear. Okay. So I have already explained about the static process. Heat interaction is equal to work interaction for isothermal process. So all the formula for heat interaction will be same as work interaction. Heat will be equal to P1 V1 log of V2 by V1 is equal to P1 V1 log of P1 by P2. So you can use this formula for finding the heat in constant temperature process. In polytropic process, the heat transfer is different. Why? In polytropic process, the heat transfer is equal to polytropic work into gamma minus N over gamma minus 1. This is a formula for heat transfer in polytropic process. So it is a very important formula. And in polytropic process, the work transfer becomes greater than the heat transfer. It is only an exception. एक exception है that in polytropic process, the heat transfer becomes greater than the work transfer. Work becomes greater than heat, and du will become negative. And because the internal energy becomes negative, the polytropic specific heat becomes negative, which is gamma minus n by n minus 1. This is the polytropic specific heat. Why it is negative? Because in polytropic process, the work will be more as compared to heat. So how you are getting more work in polytropic process? By consuming your internal energy. Your internal energy will decrease to give work in polytropic process, because in polytropic process you require more work than the heat given in polytropic process. Okay. So conclusion is, in isothermal process, work done by system is equal to heat supply. That is very important. And in polytropic process, work done by system is exceed the amount of heat supplied to the system. So these are the two important relations that is you have to remember. Next is free expansion process. Free expansion or Joule expansion. This is an experiment done by Joule, who gave the first law of thermodynamics. It is also called unrestrained expansion. Okay. जिसमें किसी भी तरह का restraint नहीं है. There is no constraint or restraint. Okay, so we are having two containers. Both are insulated, completely insulated. No heat transfer, no chance of heat transfer to take place. One is in vacuum and other is having some ideal gas. So there is no heat transfer, chance of heat transfer. One is in vacuum, other is having ideal gas, and both are basically having a partition. Now suddenly if this partition is removed, suddenly the gas will escape quickly into the other chamber. This is what happens after this partition has been removed. Okay, so as you quickly open this wall, the gas from this side will quickly escape into the other side, and there will be no work which will be done on the system. So work transfer will be zero in that case. Heat transfer work is zero, so change in internal energy will be zero, because it is a closed system and it is a highly irreversible process of closed system. Highly irreversible process. Now my dear students, you must be thinking that change in internal energy is zero, so initial is equal to final internal energy. So initial temperature is equal to final temperature. So is this free expansion process is an isothermal process? No. Free expansion process is not an isothermal process, because the initial temperature is final temperature. Initial temperature may be equal to final temperature, but intermediate temperatures are not same. Intermediate temperatures are different. In isothermal process, temperature remains constant throughout the process, but in free expansion process, the intermediate temperature are different. Intermediate temperature are different. So that is why free expansion process is not an isothermal process, because intermediate temperature is not same, while initial and final temperature is same. Okay. Now let's study about first law of thermodynamics for open system. In open system, the first law of thermodynamics you will be studying about steady flow energy equation. One is called steady flow energy equation, one other is called unsteady flow. The steady flow energy equation will be studying in first law of thermodynamics. In that you will be studying about very important thing, that is what is the meaning of steady? Something which if quantity does not changes with time. अगर आपकी quantity time के साथ change नहीं करती है, then it is called as steady. Something which does not changes with time is called steady. Okay. So in steady flow analysis, two things will be followed. One is conservation of mass. Mass will be conserved in steady flow energy equation analysis in open system. Another is conservation of energy. Energy will be conserved. Okay, these two things will be followed in the steady flow energy analysis. And the final result you will be getting here is this. This is the final result you will be getting in steady flow, first law of thermodynamics for open system. So this is the equation you have to remember. That is mass. And one more important thing, because mass is conserved, so mass at the inlet is equal to mass at the exit is equal to m. Let us say that. And total energy at the inlet is equal to total energy at the outlet. Okay. So all the types of energy, whether it is potential energy, whether it is kinetic energy, internal energy, heat energy, work, all these energy come entering the system and leaving the system, that will be equal. This is conservation of energy, this is conservation of mass. So this is the steady flow energy equation you will be getting here. Now my dear student, there is a very important thing I want to tell you for this equation. In this equation, this is mass. Generally it is given in kg per second. If it is given kg per second, then all these quantity must be in kilowatt, or this will be in kilojoule per kg. This will be in kilowatt. This will be in kilowatt. Now what important thing is here, that my dear student, they are in kilojoule per kg, but these two are in joule per kg. If you want to add two quantities, then this has to be converted. Kinetic energy has to be converted in kilojoule per kg by dividing by 1000. So they have to be divided by 1000. Why? Because I want to convert this into kilojoule per kg. Okay. So I have to divide by 1000 because this is always in kilojoule per kg. Enthalpy, specific enthalpy. Okay. So always remember that this mistake is done by most of the students, that they don't understand that why you need to divide by 1000 here, because the enthalpy is in kilojoule per kg. This is in kilowatt. This is in kilowatt. They are, if you don't divide by 1000, they will be in joule per kg. You have to divide by 1000 so that the unit become equivalent. Okay. So this is a very important, this is the steady flow energy equation you have to remember. Steady flow energy equation you have to remember, my dear students. Okay. अगर आप ये नहीं लगाते हैं तो गलत हो जाएगा. Okay. Remember that. Now, if you apply some assumptions on different devices like turbine, compressor, nozzle, diffuser. So in the case of turbine, the work output of turbine, the work output that you get from the turbine will be equal to enthalpy at the inlet of turbine minus enthalpy at the outlet. For example, in case of Rankine cycle, the work output of Rankine cycle will be equal to enthalpy at the inlet of turbine minus enthalpy at outlet of turbine. That is the work output of Rankine cycle. Compressor work is equal to enthalpy at the exit of compressor minus enthalpy at the inlet of compressor. This is the compressor work. While nozzle and diffuser, this is not the steady flow energy equation. The final energy equation is this. This is the energy equation for nozzle and diffuser. If you don't divide by 1000, then you will get wrong result, because they will always be in kilojoule per kg, and these two are in joule per kg. So you have to divide by 1000, sorry. Okay, this is the steady flow energy equation for nozzle and diffuser. For nozzle, the final velocity is very, very greater than initial velocity. So initial velocity is negligible. So final velocity will be getting as 2000 of initial minus final kinetic energy. And for diffuser, the function of diffuser is to convert the kinetic energy into pressure energy. So the inlet velocity will be very, very much greater than exit velocity. So inlet velocity of diffuser will be equal to root of 2000 of enthalpy at the exit minus enthalpy at the inlet. So this is how you find the value of the velocity at exit of nozzle and velocity at the inlet of diffuser. Okay, clear everyone? Is it clear? So from here you will be getting the velocity in meter per second in nozzle and diffuser. Yes. Next we study about the throttling devices. What is a throttling device? Throttling device is a device, example, throttling is a process in which we try to decrease the pressure. Decrease the pressure in the expense of energy. प्रेशर को कंटिन्यूसली हम डिक्रीज करने की कोशिश करते हैं, प्रेशर को रिड्यूस करने की कोशिश करते हैं, और कैसे करते हैं? बाय रिस्ट्रिक्टिंग द फ्लो. दैट इज कॉल्ड थ्रॉटलिंग. There are different types of throttling device like capillary tube you use in domestic air conditioner and refrigerator, porous plug, flow through porous plug. Suppose there is a pipe and inside this pipe we are using a porous plug. which is some kind of granular solid particles. So when the fluid will be trying to flow inside this pipe, it will be obstructed by or restricted by the presence of this porous plug, and because of that the pressure of the fluid will decrease. Okay, so this is the main purpose of the throttling. Throttling is used to decrease the pressure. Partially open valve, if the valve is completely open and suddenly you partially open the valve, then the pressure will decrease. Flow through a small opening or orifice. These are all examples of throttling devices. In throttling devices, the steady flow energy equation is this: heat transfer, work, everything is zero. Only thing is that the initial enthalpy is equal to final enthalpy. So throttling process is also called isenthalpic process. It is also called isenthalpic process, throttling process. Okay, so there are different types of characteristics of throttling process. For example, it is an isenthalpic process, enthalpy remains constant, it is highly non-quasi-static, it is irreversible process, heat transfer, work is zero. These are the important characteristics of throttling process. Now let's talk about the unsteady flow. Let's talk about the unsteady flow. It is very important. Unsteady flow means the flow rate is changing with respect to time. If the quantity changes with respect to time, that is called unsteady flow. In the unsteady flow, the mass conservation of mass and conservation of energy. This is what that is the total energy will be conserved, but energy at the inlet will not be equal to energy at the exit. That is not possible, because the energy at the inlet minus energy at the outlet will be equal to some energy which is accumulated. There will be some energy which will be stored inside the system. Okay, accumulated inside the system. Similarly, the mass at the inlet minus mass at the exit will not be zero. It will be equal to some mass which will be accumulated, which will be stored inside the system in the unsteady flow. Okay, so in the unsteady flow, the mass at the inlet minus exit is not equal to zero. Same applies to energy. So this is the energy equation for unsteady flow. You have to remember. In the unsteady flow, the final equation you will be getting this: if changes in kinetic energy and changes in potential energy are zero, are neglected, and the energy, total energy is equal to only total internal energy is equal to total internal energy. अगर आप इस टोटल एनर्जी को क्या कर दो, इंटरनल एनर्जी के इक्वल कर दो, then this will be equal to du by dt is equal to mihi plus dq by t minus this. Okay, this is the equation you will be getting for unsteady flow. This is the unsteady flow equation. In open system, first law of thermodynamics for unsteady flow. Okay, so if kinetic energy and potential energy is negligible and the total energy is equal to internal energy, then this is the equation. Now, what are the application of the unsteady flow? One is bottle filling process. When you are filling a bottle, so important result I am telling you, only the important result. When the application of the unsteady flow is the filling of a bottle, in that the final temperature becomes equal to gamma times of initial temperature. This is the final result you get from a bottle filling process application. Okay, that is the final temperature will be equal to gamma times of initial temperature, or final internal energy will be equal to initial enthalpy. Okay, so from here you will be getting CV T2 will be equal to CP T1. Okay, so T2 will be equal to Cp by Cv of T1. So T2 will be equal to gamma times T1. This is a very important result. Next application is charging or discharging of a tank. In charging and discharging of tank also you will be using unsteady flow energy equation. So the final result you will be getting that in discharging from a tank, the heat transfer will be zero. It will be an adiabatic process. Okay, and in case of charging a tank, for example, in charging your tank or your, for example, if you want to charge your, for example, you go to a petrol pump to charge your car with some petrol. Okay, so that is example of charging a tank. In that also the final temperature will be equal to gamma times of initial temperature. Okay, the same result you will be getting for charging a tank that you have got for filling a bottle. Okay, now let's come to second law of thermodynamics. Second law of thermodynamics you will be studying about two things. One is called, it is also called qualitative, it talks about energy as a qualitative form. Qualitative, or it talks about different grades of energy. It talks about grades of energy, and basically it says that heat is a low grade energy, and work, which is mechanical energy, is a high grade energy. High grade energy. It talks about the quality of the energy. First law of thermodynamics talks about the energy quantification, and the second law talks about the quality of the energy. It talks about the grades of the energy. Like work is a high grade energy and heat is a low grade energy. If we always want to have high grade energy, nobody wants to have low grades. Do you want low grades in your exam? No. You always want to have high grades in your exams, right? So work is a high grade energy. For example, electrical energy. Electrical energy is the high grade energy you want from any type of power plant or in any type of, for example, in an automobile you want mechanical energy so that your automobile can move, right? So we always want to convert this heat into work. So that is what second law of thermodynamics talks about. It talks about the grades of energy, and it has two statements. One is Kelvin-Planck statement. Kelvin-Planck statement. Another is Clausius statement. Kelvin-Planck statement basically talks about the heat engine. Heat engine has been given by Kelvin-Planck, and Clausius has given the concept of refrigerator and heat pump. Okay, so what does Kelvin-Planck says? Kelvin-Planck says that if you want to, it is impossible for any device to exchange heat with a single reservoir and convert it into work without rejecting some heat to another reservoir. Okay, so this is basically said by Kelvin-Planck. Kelvin-Planck says that if a device is working in a cycle, it is impossible for a device to exchange heat with only a single reservoir and develop some work and without rejecting any kind of energy as heat. Okay, so this is Kelvin-Planck statement which gave the concept of heat engine. So in that we'll be having a source which will be having some temperature. It is a high temperature reservoir which rejects some heat to an engine or device. It supplies some heat to a device, and by that this device will be doing some work. But as first law of thermodynamics, second law of thermodynamics says that Kelvin-Planck statement, you cannot convert this heat entirely into work. Some heat has to be rejected. Okay, to what? To a low temperature reservoir which is T2, which is sink here. So this is a heat engine, and the efficiency of the heat engine is equal to 1 minus heat rejected by heat supplied. So this formula will be used for both reversible as well as irreversible heat engine. Okay. Next is concept of refrigerator. एक क्वेश्चन था, देखिए क्वेश्चन अगर आपके गेट से रिलेटेड है वो मैं आपको आंसर करूंगा, डोंट वरी. On 28th of December, I will be having only a session only on practice of thermodynamics question. In that you can ask any questions. Okay. Concept of refrigerator. See, Clausius statement says that if you want to transfer heat from a low temperature to high temperature, naturally it is not possible because natural tendency for heat is to flow from high to low temperature. So if you want to transfer heat from low to high temperature, you require some external work as input. So based on that, we have the concept of refrigerator and heat pump. Concept of refrigerator and heat pump is given by Clausius statement. Okay, now let me talk about PMM2 also, because we are talking about this. Let us talk about PMM2 also. What is PMM2? PMM2 is basically a device which says that it is a hypothetical device which takes heat from a single reservoir and convert that heat entirely into work. This kind of hypothetical device is called PMM2. It is a hypothetical device which converts the entire heat taking from a single reservoir and convert it into work. And this hypothetical device actually violates Kelvin-Planck statement. It violates the Kelvin-Planck statement of second law of thermodynamics. Okay, clear everyone? So PMM2 is basically a hypothetical device which violates the Kelvin-Planck statement of second law of thermodynamics, because it is a device which takes heat from a single reservoir and convert that heat entirely into work. Okay, this type of hypothetical device is not feasible according to Kelvin-Planck statement, because some heat has to be rejected. It is not possible to convert entire heat into work. Okay, some heat has to be rejected to a low temperature device, a low temperature reservoir, that is the sink. Okay, so PMM2 is a device which violates the Kelvin-Planck statement. Concept of refrigerator. Refrigerator is a device which takes heat from a low temperature sink, low temperature place where we have to maintain a low temperature. It will absorb the heat from that place where we have to maintain a low temperature, and after absorbing the heat, it will reject the heat to basically to the source okay, at a high temperature. And for that we require some work input. So COP of the heat pump is equal to, or refrigerator is equal to desired effect by work input. Now here the desired effect in refrigerator, this is the desired effect. This is the desired effect in case of refrigerator. So desired effect is this divided by work input. Now work input will be equal to heat rejected minus heat supplied. It is equal to heat rejected minus heat supplied. Why? Because work output is equal to heat supplied minus heat rejected. So work input will be equal to heat rejected minus heat supplied. This is very, very important. Okay. For heat pump desired effect will be this. Only difference between heat pump and refrigerator is the desired effect. This is the only difference between heat pump and refrigerator. This is the desired effect. Okay. So COP of a heat pump will be equal to QH by QH minus QL. There is a relation between COP of heat pump and refrigerator. COP of heat pump is equal to 1 plus COP of refrigerator. One more thing, important thing. COP of heat pump is equal to 1 by efficiency of the heat engine. This is also very important relation. This question comes halfway past 45 minutes only more. No, 45 minutes, already 15 minutes extra I have taken. The lecture was only for 90 minutes. Already I have taken extra 15 minutes, so I will try to, let's see how much we can go. I thought that I can complete entire thermodynamics in 90 minutes, but as you can see, it is becoming very difficult. Let's see how much we can go with this. COP of heat pump is equal to 1 by efficiency of the heat engine. It is very, very important relation. And COP of heat pump is equal to 1 plus COP of refrigerator. These two relations are very, very important, especially for solving the numericals of second law of thermodynamics. These relations are very, very important. Okay. Now, one question comes in the exam that there is an engine and you are reversing that engine and converting that into into a device which takes work as input. You have to find the COP of reverse Carnot cycle. So, what is reverse Carnot cycle? Will tell you about that. Don't worry. For right now, you have to remember this relation. COP of heat pump is equal to 1 plus COP of refrigerator, and COP of heat pump is equal to 1 by efficiency of heat engine. Now, let's talk about Carnot cycle. Carnot cycle is the working cycle. It is a working cycle for all the standard, not working cycle. It is a standard cycle for all heat engine. Why standard? बेटा स्टैंडर्ड का मतलब होता है कि जैसे हम कहते हैं ना आपके लिए स्टैंडर्ड है, लेकिन स्टैंडर्ड है बट इट इज आउट ऑफ योर रीच. You cannot achieve it. It is a standard, but you cannot reach up to that level. So that is why it is called a standard. It is a standard cycle for all heat engine. All the heat engine try to become Carnot, but they cannot become Carnot. Okay. So what is a Carnot cycle? Carnot cycle is a cycle which consists of different types of process. These processes are represented here with the help of pressure, volume, and temperature and entropy diagram. These processes are reversible isothermal heat addition, reversible adiabatic expansion, reversible isothermal heat rejection, and reversible adiabatic compression. These are the 4 processes in Carnot cycle. Now, very important thing is that in Carnot cycle we are having 2 isothermal process, 2 isothermal and 2 isentropic or reversible adiabatic process. Both these processes are difficult to achieve. Both these processes are very difficult to achieve. Why, my dear students? Because isothermal process is a very slow process. If we have to achieve this process in real, then process has to be carried out very slowly in real. An isentropic process means adiabatic, reversible adiabatic process. Adiabatic process in real, you have to do it very fast, in a very fast manner. A process which occurs very fast, a process which occurs very slow. It is not a problem still, but let us say this is a very slow process. Now, this is isothermal. Again a very fast process. Again a very slow process. Again a very fast process. My dear, is it possible that in a cycle, you have to run, first you have to walk slow, then again very fast, again slow, again very fast? It is not possible for ideally it is not possible for any cycle to do like that. Okay. A process which is carried out very slowly, again very fast, again slow, again very fast, it is not possible to work in a cycle. In a process, it is possible to carry out isothermal and isentropic process. But In a cycle, it is not possible to have a process which is very slow and very fast. Not possible. That is why Carnot cycle is very difficult to achieve, my dear students. Carnot cycle जिसको father of thermodynamics ने दिया था. Father of thermodynamics. Who is father of thermodynamics? It is Sadi Carnot. Sadi Carnot is the father of thermodynamics. Who has given this Carnot cycle? He has given this Carnot cycle. So he has given this Carnot cycle. It is a standard cycle for all the heat engine. All the heat engine look up to this cycle. They want to become this cycle, but it is very difficult to become this cycle because this cycle is not practically feasible. Okay. So there are some important points which are related to Carnot cycle. Now, efficiency of a Carnot cycle. There are some important points. Efficiency of the Carnot cycle only depends on two things: lower and higher temperature limits. Efficiency of the Carnot cycle depends on these two things. The temperature at which heat is rejected, this is a minimum temperature. Let us say this is lower temperature. Temperature at which heat is applied, this is a higher temperature, TH. So efficiency of the Carnot cycle only depends on the lower and higher temperature limits. Okay. So my dear students, there are some Carnot principles which are very important. There are two Carnot principles which are important. Let us say we are having two temperatures source. One is source, one is sink. Okay, and between the two temperature source and sink reservoir, we are having, let us say, two reversible cycles. Both are reversible devices. Both are reversible. So efficiency of both the reversible devices, if they are both reversible, operating between same temperature limits, then efficiency of both reversible devices will be equal. Let us say this is device 1, this is device 2. So efficiency of these two engines will be equal if they both are reversible engine and operating between the same temperature limits. This is one Carnot principle. But if between same temperature limits, if you are having one reversible and other is, let us say, other is irreversible. This is irreversible and this is reversible, operating between same temperature limits, then efficiency of the reversible cycle will always be greater than efficiency of irreversible cycle. Okay, clear everyone? So if between two same temperature reservoir, if there are two reversible engine, then efficiency of this reversible engine will be equal because they are operating between same temperature reservoir, so their efficiency will be only depending on temperature limits. But if between same temperature reservoir, if they are one reversible engine, one irreversible engine, then efficiency of a reversible engine will always be greater than irreversible engine. This is a very, very important result. These are two Carnot principles which have been given by Carnot. Okay, remember that. Now, so there are two things which I have to tell you. I will be explaining about these points and about second law efficiency. But before that, I want to tell you about very important thing. Let us say we are having a heat engine. It is operating between temperature. Let us say it is taking some heat. It is doing some work. It is rejecting some heat to low temperature device. So what I want to explain you here, very important. There will be two efficiency. One will be actual efficiency, which will be equal to 1 minus heat rejected by heat supplied. This is actual efficiency. It is also called first law efficiency. And one is reversible or Carnot efficiency. It is equal to 1 minus T lower by T higher. Now try to understand it it's very, very important. Actual efficiency or first law efficiency. If actual efficiency is greater than Carnot or reversible, then this is impossible. If there is a device for which actual efficiency becomes greater than Carnot, then that is impossible. If actual efficiency becomes less than Carnot, let us say we are having an engine, and for that engine, the actual efficiency of that engine is less than Carnot or reversible engine efficiency, which is between temperature limits, which is formed by 1 minus T lower by T higher. So if that is possible, then this will be irreversible engine. Such an engine will be irreversible engine. And if actual efficiency becomes equal to Carnot, then such an engine will be called a reversible engine. Clear everyone? Is it clear everyone? Tell me. It is very, very important. Now comes a very, very important part. There is a term called second law efficiency. This second law efficiency will only be formed in this case. Only in this case, we find second law efficiency. सेकेंड लॉ एफिशिएंसी को हम सिर्फ इस केस में फाइंड करते हैं, सिर्फ इस केस में, हम किसी और केस में फाइंड नहीं करते. ओके, रिमेंबर दिस थिंग. सेकेंड लॉ एफिशिएंसी किस केस में फाइंड करेंगे? ओनली व्हेन एक्चुअल एफिशिएंसी विल बी लेस देन द कार्नोट और रिवर्सिबल एफिशिएंसी. इज इट ओके विद एवरीवन? टेल मी, इज इट ओके? हैव यू अंडरस्टूड दिस थिंग? When the irreversible engine will be there, only in that condition when the actual efficiency is less than Carnot, because if it is greater than, actual is greater than Carnot, it is impossible. So we don't need to find the second law efficiency. If they are both equal, then it is a reversible engine. Then also we don't need to find second law efficiency. But if it is, this is the case, then we have to find second law efficiency, which is equal to actual or first law efficiency divided by Carnot efficiency. Only in this situation we have to find the second law efficiency. Is it clear to all of you or not? It is a very, very important thing that I want to tell you, and this is what you do mistake. Most of the students do mistake in the GATE exam questions. Okay, this is a very, very important point. Second law efficiency we don't find for all the cases. Only in this case we find second law efficiency when actual efficiency becomes less than the Carnot efficiency or reversible efficiency. Now let's come to Clause's inequality. What is Clause's inequality? This is cyclic integral of del q by t is less than equal to 0. This is Clause's inequality. Okay, my dear students. Now if cyclic integral, for a cycle, del q by t, that total heat transfer divided by absolute temperature, this is 0, that it is a reversible cycle or engine. If it is cyclic integral of del q by t less than, it is a irreversible engine or cycle. And if it is greater than 0, then it is an impossible cycle or engine. Okay, so this is Clause's inequality. It is very, very important. Now let's come to what is entropy. Entropy, my dear students. Entropy क्या होती है? Entropy is defined as degree of randomness. Entropy के दो definition होते हैं. It is called degree of randomness or disorderedness. Disorderedness of molecules. Okay, in terms of physical meaning of entropy, it is called as degree of randomness or disorderedness of molecules. More is the orderness, less is the entropy. For example, ice will be having less entropy, and as the ice will convert into water will be having more entropy. Okay, so more a molecule becomes disordered, or more is the randomness of the molecules, more will be the entropy. This is the physical meaning of entropy. Physical significance of entropy, physical meaning of entropy is that entropy is defined as degree of randomness and disorderedness. More is the randomness, like gases have more randomness. Solid अगर आपका है, solid के molecules move नहीं करेंगे, they will not move. But gas molecules are always in random motion, right? So gases will be having more entropy. So entropy can be viewed as a measure of degree of disorderedness or randomness. As a molecule system becomes more disordered, the position of the molecules become less predictable and entropy will increase. Entropy of a substance is lowest in the solid phase and highest in the gaseous phase. Why? Because gases will be having more randomness, more entropy. Okay. Now a very important point, the entropy of a pure crystalline substance is 0 at 0 Kelvin. This statement you get from third law of thermodynamics. Entropy of a pure crystalline substance. Solids have very less entropy, but even a pure crystalline solid or substance will be having 0 entropy also, but only under 0 Kelvin temperature. Now question is 0 Kelvin temperature possible? No. According to third law of thermodynamics, it has got two statements. It is impossible to achieve 0 Kelvin temperature, which is also called absolute temperature, 0 Kelvin temperature in finite number of steps. Finite number of steps में तो आप 0 Kelvin temperature कभी भी नहीं पहुंच सकते. Okay, you have to do infinite. लेकिन आज तक 0 Kelvin temperature नहीं पहुंच सकते. आप 0 Kelvin temperature cannot be you can achieve in finite number of steps. This is one statement of third law of thermodynamics. Another statement is the continual motion of a machine. The continual motion of machine. My dear students, अगर आप लोग क्रिसमस मनाने के लिए जा रहे हैं, so I think हमें भी फिर सेशन को फिर एंड कर देना चाहिए. प्योर क्रिस्टलाइन मीन्स, प्योर क्रिस्टलाइन का मतलब होता है नो डिसकंटिन्यूटी और voids in a solid, then that will be called as pure crystalline solid. Okay, continual motion of machine in absence of friction is impossible. This is second statement of third law of thermodynamics. Third law of thermodynamics are having two statements. Okay, one is this and this is the another statement. A device which violates this statement of third law of thermodynamics, that is called PMM3. PMM3 is a device which violates the second statement of third law of thermodynamics. It is a device which operates in absence of friction continuously. That is PMM3. Okay. Now we have understood Clausius inequality. Del Q by T is less than equal to 0. This is Clausius inequality. ओके, डिसकंटिन्यूटी तो रहेगा ही बेटा, डिसकंटिन्यूटी रहता है सॉलिड में, बट प्योर क्रिस्टलाइन सॉलिड इज अ सॉलिड व्हिच इज हैविंग नो वॉइड्स. द मॉलिक्यूल्स आर कंटिन्यूअस, दे आर हैविंग नो वॉइड्स. किसी तरह के वॉइड्स ना हो, ऐसे सॉलिड को हम कहते हैं परफेक्टली क्रिस्टलाइन सॉलिड. बिल्कुल इस तरीके से इट इज कॉल्ड परफेक्टली क्रिस्टलाइन सॉलिड. ओके, क्लियर? So Clausius inequality we have understood from second law of thermodynamics. Second law of thermodynamics, Clausius inequality also defines entropy. So second law of thermodynamics defines entropy. Second law of thermodynamics defines entropy. How does it define entropy? Let us see that. Second law of thermodynamics also defines entropy. How does it define? Let's see that. Clausius inequality, it is for a cycle, but if you apply this Clausius inequality for a process, you will be getting this relation. The total entropy change will be equal to del Q by T plus entropy generation. I don't want to do the derivation of this, but you have to remember this relation. Total entropy change is equal to del Q by T plus entropy generation. Entropy generation is basically is a term due to which is called it is entropy generation, and it is due to internal irreversibilities. This term is due to internal irreversibilities present inside the system. Entropy is basically depends on the degree of randomness or disorderness, but entropy also depends on the irreversibilities. Entropy also depends on the irreversibility present on the system, in the system. More is the irreversibility, more will be the entropy. Okay, this term defines the external interaction. Entropy depends on two things. One is the external interaction due to temperature difference. Entropy can change because of external interaction due to temperature difference, and it can also be because of the internal irreversibility present inside the system. Okay. So this is how the entropy generation varies. Total entropy varies. Now, for internally reversible process, or for a reversible process, tell me, if we are having a reversible process, entropy generation will be 0. Will there be any entropy generation? No, entropy generation will be 0 for an internally irreversible process. In that situation, the total entropy change will only be equal to del Q by T. This is only process for a reversible process. For a reversible process, the entropy total entropy is equal to del Q by T. Like for isothermal process, isothermal process is called a reversible process. In that, the total entropy change is equal to del Q by T, because in that condition, the internal irreversibility becomes 0. Okay. Now we are going to understand different types of entropy change for a closed system. For internally reversible process, the entropy change is equal to del Q by T only. If heat is added to the system, the entropy change will be positive. If heat is removed, the entropy change will be negative. And now one important thing I want to tell you, that let's say we are having a system. Some heat is going into the system. We want to find the entropy change. The entropy change will be equal to positive. If heat is going out of the system, if you have to find the entropy change of surrounding, then that will be minus Q by T. Why? Because heat going into the system will be positive, and heat going to the surrounding, that is, heat is going from the system to the surrounding. So for the system it will be negative, but for surrounding it will be positive. So if we have to see for what we have to find the entropy. If we have to find the entropy for the surrounding, heat is going to the surrounding, that the entropy will be positive. But if the heat is going, if you have to find the entropy of the system, then that will be negative. So let us say we are saying that heat is going to the surrounding. Then for surrounding, the entropy change will be positive Q by T. And for system, the entropy change will be equal to negative Q by T. So we have to see whether you have to find the entropy change of system or surrounding. For adiabatic process, the entropy change, if Q becomes 0, the entropy change will become 0. In that condition, the entropy will become constant. It is only case that internally reversible adiabatic process undergone by a closed system is always isentropic. Okay. It is a very, very important relation, that internally reversible adiabatic process. Sometimes they will not use the word internally. They will simply say reversible adiabatic process are always isentropic. But isentropic process cannot be called as always reversible adiabatic. Why? Because for internally irreversible process, the entropy change is equal to del Q by T plus entropy generation. And for internally irreversible process, entropy generation is always a positive quantity. So if heat is added to the system, the entropy change will be equal to positive Q by T plus entropy. So it will be always a positive quantity. If heat is removed from the system, then entropy change can be positive, it can be negative, it can be 0. Why and how? Because entropy generation is always a positive quantity. We don't know what is this positive quantity value, and also we don't know what is the amount of heat removed from the system. If the heat removed from the system becomes less than the entropy generation value, then this value entropy change will be positive. If heat removed from the system is greater than entropy generation value, then entropy change will be negative. If heat removed from the system becomes equal to entropy generation value, then entropy change will be 0. So in the case of heat removed from the system in internally irreversible process, there comes a case when entropy change can also be 0. That is why we cannot say that isentropic process is always reversible adiabatic, because in this particular case also the entropy change can become 0 and process can become isentropic process. Okay, but reversible adiabatic process is always isentropic. Last case is adiabatic process are internally irreversible. In this particular condition, if heat transfer becomes 0, the entropy change will be equal to entropy generation is equal to, okay. So in that condition, entropy change will always be positive. That is, internally irreversible adiabatic process always has positive entropy. Why entropy generation is always positive quantity? Because entropy generation is the source for the irreversibility. Entropy generation is always causes irreversibility. So because of entropy generation, it is not, see, entropy generation can either be positive or it can be zero. It can never be negative because it is entropy principle which says that the total entropy change of the universe is equal to entropy generation. For a reversible process, entropy generation can become zero. But for irreversible process, it is always positive because entropy of universe can never decrease. Okay? Because total entropy change of the universe is equal to entropy generation. Let's see that. Increase of the entropy principle says that the total entropy of the universe always increases. Okay, so total entropy change of the universe will be equal to this. Now, in the case of universe is an isolated system. So entropy change of the universe will only be equal to entropy generation. Right? Now, if in the universe we are having reversible process, if in the universe we are having some reversible process, only reversible process take place in the universe, then entropy change of the universe can become zero also. Why? Because entropy generation becomes zero. And in the case, if in the universe we are having irreversible process, then entropy generation will all, and the universe entropy change of the universe will only be equal to entropy generation. So entropy of universe will be equal to positive quantity. मतलब कहने का मतलब ये है that if inside the universe we are having only reversible process, then entropy change of the universe will be zero. And if inside the universe we are having irreversible process, the entropy of the universe will always be positive. So in the universe, only those processes are possible for which either entropy change is zero or positive for the universe. If entropy of the universe becomes negative, it is impossible. It is impossible that entropy of the universe can become negative because universe is always expanding and the irreversibility in the universe is always increasing. So universe will be having always a positive value of entropy. So irreversibility will always be present inside the universe because randomness, if you talk about randomness, there is very much high randomness in the universe. Okay. So universe is always expanding and so the entropy of the universe is always increasing. If the entropy of the universe becomes negative, it is impossible. It is always either entropy of the universe, entropy change of the universe is either greater than or equal to zero. It can never be less than zero. Okay, clear everyone? It is very important. Now my dear students, so this is very important. If the process is reversible, entropy remains constant. If it is irreversible, entropy of the universe will increase. Hence, according to second law of thermodynamics, all those processes are possible for which increase in the entropy of the universe is either zero or positive. Okay, this is a very important conclusion. Alright, now entropy change of the universe is also equal to entropy change of the system plus entropy change of surrounding. This is very important thing. And total entropy change of the universe is sum of entropy change of system plus surrounding because universe comprises of both system and surrounding. Okay. Now for a reversible process, the entropy change is equal to what? Del Q by T, right? So we can say that for reversible process the Q will be equal to T into ds. So if you plot a graph between temperature and entropy, then the area under this graph will be giving you the total heat transfer because it is equal to T into ds. But it is only possible for a reversible process. So for a reversible process, area under temperature entropy diagram gives you heat transfer. Like for reversible process, area under PV diagram gives you work transfer. So area enclosed by internally reversible process gives net heat transfer. Okay. Therefore, for internally reversible process, area enclosed by PV and TS diagram are same. Okay, for internally reversible cycle के लिए area enclosed by PV and TS diagram will be same because heat will be equal to work for reversible cycle. For reversible cycle, area under the PV and TS diagram will be same. So if we are having two reversible cycle, both are reversible cycle, and the area under the both cycle will be equal. Now we are coming to very important thing that the slope of temperature on entropy but is dt by ds at constant pressure is equal to T by Cp, and dt by ds at constant volume is equal to T by Cv. And the slope of constant volume is always greater than slope of constant pressure on temperature entropy diagram. That is, Cv will always greater than, this is how you will be having, okay, that is the slope of temperature versus entropy for constant volume will always be greater than constant pressure. Okay, so this you have to always remember that. If you have to plot constant pressure and constant volume process on temperature entropy diagram, if you have to plot these two processes, then the constant volume diagram will be having more slope than constant pressure. This is very, very important result. You have to remember that the slope of constant volume will be greater than constant pressure on temperature entropy diagram. Okay. Like in the case of Carnot cycle also, you must have seen that if you have to plot the constant volume and constant pressure on same graph, constant volume will be having more slope as compared to constant pressure. There are two TDS equations which are important. TDS is equal to du plus pdv and TDS is equal to dH minus vdp. These are the two equations which have been formed by using both first law and second law of thermodynamics. Okay, they have been formed by combining both second law and first law. So these are the two TDS equations which are important, and they are two for ideal gas. For ideal gas, there are some equations which are important. Entropy change for an ideal gas is equal to Cp log of T2 by T1 minus R log of, this is a specific entropy change. Okay, R log of P2 by P1. If we have to find the entropy change, we have to multiply by mass. A specific entropy change will be equal to Cv log of T2 by T1 plus R log of V2 by V1. And specific entropy change will be equal to Cv log of P2 by P1. These are the three important formula you have to remember. Sorry, Cv log of P2 by V1, so Cp log of V2 by V1. Okay, these are the three important formula you have to remember. These are very important formulas for finding the entropy change for an ideal gas. Okay, so remember these formula, they are very, very important. So when we'll be solving the questions on Monday we will be having a practice session on thermodynamics where I'll be solving 40 plus questions of thermodynamics. So these are very important relation. Entropy change, specific entropy change. If you have to find total entropy change, you have to multiply by mass. Okay, these are the two TDS equations. Clear है सभी को? clear है? Now my dear students, there are very special case of mixing of two incompressible fluids. Mixing of two incompressible fluids. Okay, in this case we will be having two cases. One is when work transfer is zero. When we are having mixing of two incompressible fluid and work transfer is zero, in that condition, or we can say adiabatic mixing of two incompressible fluid, adiabatic mixing of incompressible fluid, and work transfer is zero in this situation, the total entropy change will be equal to m1c1 log of T final by T1 plus m2c2 log of T final by T2. This is the formula for total entropy change you will be getting for adiabatic mixing of two incompressible fluids. This is a very important formula. And the final temperature will be equal to m1c1 T1 plus m2c2 T2 divided by m1c1 plus m2c2. If the bodies become identical, if two bodies are identical here, in that situation, your final temperature will become arithmetic mean of these two temperatures. Before, okay? These are the very important results. The total entropy change is equal to, the total entropy change will be equal to m1c1 log of T final temperature by initial temperature of this system 1. And this is another, this is system 1, let us say, and this is system 2. Okay, there are some gases, let us say there is some incompressible fluid, let us say some liquid in both the system. Suddenly if these two systems becomes mixes, what will happen? There will be some increase of entropy because work transfer is zero here. Work transfer is zero, that means all the energy goes into increasing the entropy. The total entropy will be this in that situation. If the bodies become identical, the final temperature will become equal to T1 plus T2 by 2. You have to put this final temperature here and you have to solve the question. There is another case when we are mixing two incompressible fluids with maximum delivery of work. If work is maximum, you are obtaining maximum work. Then entropy, it is only possible if entropy change is zero. Total entropy change is zero, only then you can find that maximum work. Okay. Maximum work can only be obtained from a heat engine or any device when there is no entropy change during the process. Only then you can find the maximum work. Okay. So if entropy change becomes zero, in that situation the final temperature becomes root of these two temperatures. In that situation the maximum work will become Cp of or C of root of T maximum minus T minimum whole square, or it is equal to C of T1 minus T2 whole square. Okay, this is how you will be finding the maximum work in this condition. So when we are having mixing of two incompressible fluids and we are getting maximum delivery of work, then in that case entropy change will be zero. And if the bodies are identical, then the final temperature will become geometric mean of the two temperatures. Okay, this is very important case. Now let's come to another topic, which is availability and irreversibility. What is availability? Availability is defined as the maximum available work that you obtain when the final state becomes a dead state. Dead state means equilibrium with surrounding. In equilibrium with surrounding. When the final state becomes in equilibrium with surrounding, then it is called as dead state. Okay, so if you are undergoing a process, अगर कोई process हो रहा है जिसमें आपकी जो final state है, the final condition of pressure, temperature and all the other properties becomes equal to the surrounding conditions, then that is called dead state. The final state becomes dead state when it becomes equilibrium with surrounding. Now in that situation, the work that you will be obtaining from this process, that work will be a maximum work. Okay, that work will be called as maximum work, and that maximum work will be called a maximum available work or available energy. Suppose we are having a heat engine. You have found some source of heat and you are giving that heat to a heat engine, and by that heat it is doing some work W. Now if you want to obtain the maximum work, let us say the temperature is T1 here. If you want to obtain the maximum work from this heat engine, how can you obtain the maximum work? You can obtain the maximum work from this heat engine if the lower temperature, let us say this is T2, the lower temperature T2, see efficiency of the Carnot cycle is equal to 1 minus lower temperature by higher temperature. Okay, so if you want to get maximum efficiency from this engine, the lower temperature has to decrease. How much it has to decrease? It has to become equal to surrounding temperature. If you get it equal to surrounding temperature, you will be getting the maximum, and this efficiency will become almost maximum, that will be 1 minus T0 by T1. And in that condition, the work you will be getting when the T2 will become T0 or become equal to surrounding condition of temperature, the work you will be getting in that situation will be equal to efficiency into heat supplied. That will be equal to 1 minus T0 by T1 into Q. That work will be called the maximum available work of this heat engine. Okay, clear everyone? So if there is a heat engine, it is accepting some heat from any energy source, and by using that heat it is doing some work. If you want to obtain maximum work from this heat engine, it is only possible if the final state, if the temperature at which heat is rejected, that temperature becomes very minimum. How much it can become minimum? It can become equal to surrounding temperature. Temperature of the surrounding or atmosphere. In that situation, you will be getting maximum work, maximum efficiency, and maximum work will be getting from here. Okay. So this is how you find the maximum work for an engine. A heat engine will be equal to Q times of heat supplied into 1 minus surrounding temperature divided by the temperature of the source. Okay, this is how you find the maximum work for the heat engine. If you rearrange the term, you will be getting this as Q minus Q T0 by T1. You can also write it as Q minus T naught into Q by T1. This, my dear students, this is the entropy. This is equal to Q minus T naught into ds. Okay. When you apply this formula for maximum work, this formula is used for finding the maximum work for a process, for a system. For a system undergoing a process, this formula will be used for finding the maximum work. Q, heat supplied minus T naught into ds. This Q is the total energy. It is the total energy. And this is the unavailable energy. Unavailable energy. If you subtract the total energy, from total energy, if you subtract the unavailable energy, which is also called as irreversibility, you will be getting the maximum available energy. So maximum available energy is equal to difference of total energy minus the unavailable energy. For example, this will give you the total heat supplied, and this will be the total heat rejected, or this is the unavailable energy. And from the area under this will be giving you the total available total energy. Total energy will be equal to this red. And this is the unavailable energy. So this energy will be the available energy. If you subtract the total energy minus unavailable energy, you will be getting this energy, which is the available energy. Okay. So this is how you find the maximum available work for the heat engine. This is how you find the maximum available work for a system undergoing a process. You have to find the entropy change, multiply with the surrounding temperature, and subtract this total quantity from the heat, total heat. You will be getting the maximum work for the system. Okay. Now there are some important formula we use for available energy. Suppose that there is a system, there is a heat engine which is at different temperature. One heat engine is accepting the heat. It is doing some maximum work by rejecting the heat to surrounding. And there is another heat engine which is at different temperature, T2. Okay. It is also rejecting the heat to the surrounding. It is also developing some maximum work. But if you compare these two engines, the temperature T1 is greater than T2. In that situation, डिनर हो गया? डिनर तो नहीं हुआ बेटा, डिनर तो क्रिसमस के बाद ही होगा. अब तो मैं सोच रहा हूं कि आपको अवेलेबिलिटी इरिवर्सिबिलिटी खत्म कर देता हूं. एंड द लास्ट टॉपिक, प्रॉपर्टीज ऑफ प्योर सब्सटेंस, विल कवर ऑन we will cover that let's say tomorrow we'll cover the topic of properties of pure substance and ideal and real gases, because we don't have much time, because already we have taken a lot of time. I don't think complete thermodynamics will be completed. Let's see, let's try that, let's try to complete. Okay, so this, let us say there are two different types of heat engine. One is at temperature T1, other is temperature T2. Okay, now both of them are developing some maximum work, but the maximum work of this engine will be greater than maximum work of the other engine. Difference of these two maximum work will give you loss of available energy. Loss of available energy. So loss of available energy is equal to loss of the direct formula. I'm telling you the direct formula. Loss of available energy is equal to T naught into Q. Let us say both engines are supplied with same heat Q. 1 by T2 minus 1 by T1, where T2 is less than T1. Okay, this is the direct formula for finding the loss of available energy. Okay, क्लियर है? लॉस ऑफ अवेलेबल एनर्जी को फाइंड करने का डायरेक्ट फॉर्मूला होता है ये. वन मोर फॉर्मूला फॉर फाइंडिंग द लॉस ऑफ अवेलेबल एनर्जी और इरिवर्सिबिलिटी इज दिस. समटाइम्स फॉर द हीट इंजन it might be possible they can give you some work, actual work of the engine can be given, and they can ask you to find the irreversibility. Let us say this is T1, this is T0. Actual work of the engine is given. Let us say something is given and they can ask you to find the irreversibility. In that condition, irreversibility is equal to reversible work minus actual work. Okay. Reversible work is, maximum reversible work is Q times of 1 minus T naught by T1. And if we subtract from this reversible work, this actual work, you will be getting the irreversibility. So, okay, fluid mechanics revision session is tomorrow. Tomorrow and day after tomorrow at 5 p.m. we are having the entire fluid mechanics revision. Entire fluid mechanics revision will be on Saturday and Sunday at 5 p.m. Yes, already it has been planned. Already it has been planned. Okay. So irreversibility is equal to maximum work minus actual work. Now let's see availability function. Availability function for closed system is equal to U minus Ts plus P naught V. This is how you find availability function of open system. Okay. Or it is also equal to, change in availability function for closed system is equal to U1 minus U2 minus T naught of S2 minus S1. This is how you can find the change in availability of the closed system. And by finding the change in availability of the closed system, you can find the maximum available work. Maximum available work for closed system is equal to difference of the availability function for closed system. Availability function for open system is equal to H minus Ts plus mv square by 2 plus mgz. This is the total availability function for open system. But the difference of the availability function of open system will give you the maximum work, which will be equal to H1 minus H2 minus T naught of S2 minus S1. Okay. So this is how you can find the total available maximum work from the availability function of open closed system. But availability function of closed system is equal to U minus Ts. This is called Helmholtz function. If you neglect the external, this is external work. If you neglect this work, you will be getting this. This is the Helmholtz function, and G is equal to H minus Ts. This is the Gibbs function, availability function of open system. Irreversibility is equal to T naught into entropy change of universe. This formula is called as Gauss-Stodler theorem of irreversibility. Gauss-Stodler theorem of irreversibility says that the total irreversibility is equal to T naught into entropy change of universe. Total entropy change of universe. This is the Gauss-Stodler theorem of irreversibility, which says that total entropy change is directly proportional to entropy change of the universe. Clear, everyone? Now, next is pure substance. What is a pure substance? A pure substance is a substance said to be pure substance. It is of homogeneous chemical composition. Homogeneous means having same phase throughout. Having same phase throughout, that is called homogeneous. And what is heterogeneous? Heterogeneous means having mixture of two or more phases. That is called heterogeneous system. Okay. Example of a homogeneous system will be gaseous air. Or pure substance is gaseous air is a example of a heterogeneous system. Homogeneous system, which is a pure substance. Mixture of water and water vapor, mixture of ice and water, mixture of sugar and water before boiling point of water. They all are example of pure substance. But mixture of gaseous and liquid air is not a pure substance. That is a very important thing. Gaseous and liquid air is not considered to be pure substance. Both are heterogeneous, but they are not called to be pure substance. But mixture of water and water vapor, they are also heterogeneous. Even a heterogeneous mixture can be a pure substance, like water and water vapor and ice and water. Okay. Mixture of refrigerant behaving as a pure substance are azeotrophs. These are the mixture of refrigerant which behave as a pure substance, and they have unique boiling point. They have unique boiling point or single boiling point. Okay. Now, Gibbs phase rule is very, very important. P plus F is equal to C plus 2. P defines the number of phases. P defines the number of phases. For example, solid, liquid, and gases. These are the three phases you study in thermodynamics. Although we have plasma phase also, but we don't study plasma. F is the degree of freedom. Okay. So degree of freedom is very, very important. C is the number of components. So this is the Gibbs phase rule, which is very, very important. Okay. So by the Gibbs phase rule, we get some very important result. These results are at triple point, all three phases are present. All three phases are present on critical point, that is solid, liquid, and gases. They are in equilibrium. And at triple point, degree of freedom becomes 0. But degree of freedom also becomes 0 at critical point. Critical point, it is a point where saturated liquid and vapor line meet, or it is a point at which liquid and vapor are indistinguishable. Liquid and vapor phases are indistinguishable. At this critical point, both the liquid vapor are together present. They are present together. That is called critical point. At critical point, latent heat becomes 0. Latent heat, what is the latent heat? Is that heat which is required for phase change process. For example, if when you heat a liquid, it will eventually change into liquid plus vapor first, and then it will change into vapor, and then finally into superheated vapor. This is a superheated vapor. This is a superheated region. This is the subcooled region. Subcooled or compressed liquid region. And this is a wet region. Here we are seeing the phase change diagram or temperature volume diagram for a phase change from solid to liquid, liquid to vapor. Okay. And on this temperature volume diagram, if you see, triple point is actually represented by a line. So on temperature volume diagram, pressure volume diagram, and temperature entropy diagram, triple point is shown by a line. On temperature volume diagram, pressure volume diagram, and the temperature entropy diagram, on these diagram, triple point is shown by a line. While on UV diagram, internal energy and volume diagram, triple point is shown by a triangle. Triple point is shown by a triangle. And on PT diagram, by a point. So triple point will be changing its nature on different types of diagram. On temperature volume, pressure volume, temperature entropy diagram, it will be a line. On UV diagram, it will be a triangle, and PT diagram, it will be a point. Okay. At critical point, the Gibbs phase rule जो होता है ना, वो फेल हो जाता है. It fails. Why it fails? Well, because if you apply the Gibbs phase rule, P plus F is equal to C plus 2, you will not get degree of freedom equal to 0. Degree of freedom will not be equal to 0 at critical point, because at critical point also degree of freedom has to be 0, because at every point degree of freedom is 0. So at this you will be applying Gibbs phase rule will be modified, which will be P plus F is equal to C plus 1. This will become Gibbs phase rule this will be the modified Gibbs phase rule. Modified Gibbs phase rule at critical point. And at this modified Gibbs phase rule at critical point, you will be getting degree of freedom is equal to 0 at critical point. So at every point degree of freedom is 0, whether it is triple point or critical point. Okay. So critical point is the point at which liquid and vapor phases are non-distinguishable. That at critical point, both, if you heat any liquid, it will directly change into vapor, or both liquid and vapor are present together at critical point. Okay, latent heat is 0, that is enthalpy change of vaporization is 0 at critical point. And not only this is 0, hi Ankit Jaiswal, good evening. Not only this is 0, entropy change is 0, UFG is 0, everything is 0, VFG is 0, everything is 0 at the critical point. Because both liquid and vapor are sitting together at critical point. Critical point temperature of water is 374.15 degrees Celsius and critical point pressure of water is 221.2 bar. Triple point temperature is 0.01 degrees Celsius and triple point pressure is equal to 0.611 kilopascal. Okay, these are some important points you have to remember. These are the critical properties of water. Critical properties of water. Critical properties, that is at what is the critical value. Okay, clear है सभी को? Now general shape of the PV diagram. This is the PV diagram. PV diagram में आपकी जो ये curves आते हैं, these are the constant temperature lines. Constant temperature lines on the PV diagram. And on the PV diagram, the curve which passes from critical point, that is called critical isotherm. Critical isotherm is the line which passes from the critical point are called critical isotherm. And at critical isotherm, the slope dP by dV at critical point becomes 0, and also the second slope at critical point becomes 0. These are the important relation, that at critical point the first and second slope become 0 at critical point. Okay, now let's talk about, this is already we have studied. Let's talk about pressure temperature phase change diagram. In pressure temperature phase change diagram, you will be seeing all the three phases together, that is sublimation, melting or fusion, and vaporization. Okay, sublimation is a process. What is sublimation? Sublimation is a process in which solid directly changes into gas. For example, you must have seen camphor in your house. Camphor, right? Camphor, if you heat camphor, it directly changes into gas. Okay, it will not change into liquid. So sublimation is a process of changing of solid directly into vapor or gas. And vaporization is a process of changing of liquid into vapor, and melting is a process of changing of solid into liquid. And fusion is a process of changing of liquid into solid. So these sublimation is a line. Sublimation line is separate solid from gas. Vaporization line, the starting point of vaporization line is triple point, and end point of vaporization line is critical point. These are the two extreme point of vaporization line. One is triple point, other is critical point. So on pressure temperature diagram, the triple point is shown by a point. Okay. Clear everyone? Now if you see this diagram, pressure temperature diagram, there are two fusion lines, there are two melting lines. One is this, other is this, dotted one. This one is for those substances which expand on freezing, for water. Because water is a substance which expands on freezing. While substance that contract on freezing, for example carbon dioxide and other general substance जो होते हैं वो क्या होते हैं? General substances, when they freeze, they become contract. But water is a substance which, when it freezes, it expands. So this is how the variation of the graph is between fusion line is different for water and the other substance. This is a very important relation, that the slope of vaporization and sublimation line on pressure temperature diagram is positive, while slope of fusion or melting line is variable. Why it is variable? It can be positive or negative. Slope of fusion line is negative. So slope of fusion line is negative for water, and slope of fusion line is positive. Fusion line is positive for other general substance. ठीक है, सभी को क्लियर हो गया चीज? The last thing, because I cannot extend the lecture beyond, because I can give you maximum 10 minutes more, because I can understand that thermodynamics will not be completed as I thought that it will be completed in 90 minutes, but already a lot of time has been taken. So I will take 10 minutes more. I will try to tell you how to find the properties in different regions. So in a temperature entropy diagram, if you see the temperature entropy diagram, this is called as subcooled region. This is called superheated region. And this is called a wet region, which is also called liquid plus vapor region. If you heat any liquid, it will firstly change into, it will reach the saturation line, it will reach the saturated liquid line. This is saturated liquid line. This is saturated vapor line. And the point at which these two lines meet is called critical point. So what is important here is, if you heat any liquid at 1 atmospheric pressure, it will change into vapor at saturation temperature of 100 degrees Celsius, right? So till this point the temperature will be saturation temperature. Saturation temperature is that temperature at which phase change takes place. It is a constant temperature. So here latent heat will be given. Latent heat will be given for phase change. This is the saturated liquid line and this is saturated vapor line. And if you heat the saturated vapor, it will change into superheated vapor. ठीक है? Superheated vapor behaves approximately as ideal gas. Now my dear students, very important thing I want to tell you here. If the pressure will increase, अगर आप प्रेशर को बढ़ाते हैं, if the pressure increases, this is a constant pressure line, but let us say if the pressure is increasing, if pressure increases, the boiling point will increase. अगर प्रेशर को इंक्रीज करेंगे तो बॉइलिंग पॉइंट बढ़ता है, but if pressure will increase, the latent heat will decrease. If the pressure will increase, the latent heat will decrease. This is a very important thing. And at critical point or at critical pressure 221.2 bar of water, latent heat becomes zero. As pressure increases, latent heat decreases, but at critical point latent heat zero हो जाती है at critical point. Okay, this is a very, very important result. Okay, now I have to tell you about a very important term called dryness fraction. What is dryness fraction? It is equal to, suppose we are having a phase change process from liquid to vapor. If you are heating a liquid, it is changing into vapor. So this is liquid plus vapor region. Okay, this is the liquid region and this is the vapor region. So sorry, this is the superheated vapor region. ठीक है? So my dear students, what is dryness fraction? Dryness fraction is defined as the mass of the vapor divided by total mass of liquid plus vapor. But is this the formula of dryness fraction? Because in liquid plus vapor region, at this particular point, dryness fraction will be 0 and it will be equal to 1 at this on the saturated vapor line. On saturated vapor line it will be 1. Okay. So my dear students, this dryness fraction varies from 0 to 1 in the liquid plus vapor region or in the wet region. On saturated liquid line it is 0, on saturated vapor line it is equal to 1. But if you ask what is dryness fraction of steam, is it really liquid? Is it really mass of liquid? No, it is mass of the liquid water in suspension. It is not liquid, my dear. because this is the liquid region. This is liquid plus vapor region. It is the liquid will not be there in this region. It will be liquid water in suspension, or it is the water vapor in suspension. So dryness fraction of the steam, dryness fraction of the steam will be equal to mass of dry steam, mass of dry steam in this region. What is the mass of dry steam? Divide by mass of dry steam plus mass of water vapor in suspension. This is the formula of dryness fraction of steam. This you have to remember. Okay, now we are going to find the properties in different regions. If you have to find the properties in different regions, this is very important. This is a subcooled region. This is subcooled or compressed liquid region. This is a wet region, and this is a superheated region. If you have to find the properties in different regions, how can you find that? In the wet region, any property like entropy will be equal to entropy of the liquid. Let us say this is temperature entropy diagram. So entropy in this liquid region will be equal to entropy of the saturated liquid plus X times of entropy of the liquid plus, or that is entropy change of liquid and vapor. That is, this is equal to SF plus X times of Sg minus Sf. This is how you find the entropy in the wet region. And not just entropy, any property. If you have to find the enthalpy in the wet region, in this region, that is, this is region is 0.1, this is 0.2, and this is 0.3. Okay, so entropy in the region 1 is equal to this, entropy of the saturated liquid plus dryness fraction times of entropy of the saturated vapor. Okay, minus liquid. Enthalpy in this region will be equal to HF plus X times of Hg minus HF. Hg minus HF is equal to C. HFG is equal to Hg minus HF. SFG is equal to Sg minus SF. VFG is equal to Vg minus Vf. Okay, UFG is equal to Ug minus Uf. Because what is this thing? These are all properties. Property can be written as difference of the point function. Okay, properties depend on the point, because enthalpy change will be equal to enthalpy change for liquid into vapor will be equal to enthalpy of vapor minus enthalpy of liquid. Entropy change of liquid to vapor will be equal to entropy of vapor minus liquid. Specific volume of liquid to vapor will be equal to specific volume of vapor minus liquid. So this is how you can find it. Okay. So this is how you can find any property in the wet region. Vf plus X times of Vg minus Pf. Okay. So any property can be you can find in the wet region by using this formula. Clear है सभी को? clear है? बताइए. Is it clear to everyone? I can see the students has some of the students were saying sir please complete कर दो. अब complete कर रहा हूँ तो बच्चे कम हो गए. क्यों? मजा नहीं आ रहा है, मन नहीं लग रहा है. Yes, are you not enjoying this session? The session was only for 90 minutes. Now I have extended to this around 3 hours because I thought that it is not possible to complete the entire thermodynamics in 90 minutes. I thought that it is possible, but it is not possible. Okay, we have seen that. So one more important result is that the entropy change is equal to SF plus X times of SFG. Now this SFG can also be written as equal to HFG by T saturation. Sometimes in your question, sometimes in your exam, the entropy change, you have to find the entropy in the wet region, but they will not give you the value of Sg and SF. Okay, in wet region, sometimes Sg and SF not given, or let us say Sg not given. Then how can you find the entropy in the wet region? So SFG can also be written as HFG by T saturation. Why? Because in the wet region, the entropy change is equal to del Q by T. This del Q is equal to latent heat divided by saturation temperature. Okay. So my dear, latent heat is equal to what? Latent heat is the heat which is required for phase change. That is equal to, latent heat is equal to HFG. So we can write in the wet region, we can write SFG as HFG as latent heat by saturation temperature. But this saturation temperature has to be in Kelvin. Okay? Clear hai? So this is how you find the entropy in the wet region. In wet region, you can find the entropy by using this relation and this relation. Both are important. If entropy is given for liquid and vapor, you can use this relation. If they are not given, you can use this relation. Okay? Clear sabhi ko? Now comes a very important part. We are about to reach to the end of the session. Okay? So my dear students, if you have to find the entropy in this region, third subcooled region and superheated region. Let us say this is the point 2. This is the saturation temperature here. Here also it will be saturation temperature. So enthalpy in this region will be equal to, there is a term called degree of subcooling. Degree of subcooling is equal to T saturation minus T3, and degree of superheating is equal to T2 minus T saturation. This is called degree of superheating. Okay? So my dear students, let us say this is the saturation temperature is enthalpy is equal to HF, and this is, let us say, Hg. So this will be HF minus H3 will be equal to Cp of liquid T saturation minus T3. So H3 will be equal to HF minus Cp of liquid of T saturation minus T3. This is how you find the enthalpy in the subcooled region. Subcooled region में अगर आपको enthalpy find करनी है तो आप इस तरीके से find कर सकते हैं. In superheated region, the enthalpy will be equal to H2 minus Hg will be equal to Cp of vapor T2 minus T saturation. This is how you find the enthalpy in the superheated region. This is how you find the enthalpy in the superheated region. Okay, clear sabhi ko? Now, if you talk about the entropy, how can you find the entropy in the different regions? Entropy कैसे find करेंगे? Let us say this is point 2, this is point 3, this is SF, this is SG. So entropy SF minus S3 will be equal to Cp of liquid of log of T saturation by T3. So entropy in the subcooled region will be equal to SF minus Cp of liquid T saturation by T3. This is the formula for finding the entropy in the subcooled region. अगर subcooled region में entropy find करना है तो आप इस फॉर्मूले को यूज करेंगे. और superheated region में अगर find करना है, if you have to find in superheated region, then the entropy F2 will be equal to Sg plus Sg means at saturated vapor the entropy, okay, plus Cp of the vapor log of T2 by T saturation. Okay, this is how you can, ठीक है, this is how you find the entropy in the superheated region and in the subcooled region. This is how you find the entropy in the subcooled and superheated region, and this is how you find the enthalpy in the subcooled and superheated region. This is how you find the enthalpy in the entropy in the wet region. So in Rankine cycle, you will come across a statement that the process is isentropic. Rankine cycle में जैसे आपको क्वेश्चन नहीं आता है कि Rankine cycle में आपको work of turbine निकालना है, right? So when you will solve this type of questions, work of turbine you have to find. They will give you the enthalpy at this point, but enthalpy at this point will not be given. So H2 will be equal to what? HF plus X times of Hg minus HF. Okay, so you can simply find this. And how can you find X? For finding X, you can apply S1 is equal to S2. Entropy at point 1 will be equal to entropy at point 2. So this is how you will be solving the problems of Rankine cycle. Okay. So entropy at point 1 will be equal to entropy at point will be equal to entropy at point 2 will be SF plus X times of Sg minus SF. Okay. At point 2. And from here you will get the value of dryness fraction. You can put this dryness fraction here to get the value of H2. And from here you can apply the turbine work is equal to H1 minus H2. This is how you solve the problems of Rankine cycle in the GATE exam. Okay. Last thing is Maxwell relation. See, sometimes in your GATE exam you come across some 1 marks question from Maxwell equation to identify the correct Maxwell equation. See, Maxwell equation can be easily written. If you see any Maxwell equation, you will see PV is equal to TS. This term you will be getting in Maxwell equation. So if you have to write the Maxwell equation, you have to write dP by dt is equal to dt by dP. You have to write dt by dV or dV by dt. You have to write P by T, one you have to write T by P, once you have to write T by V, once you have to write V by T. To write the 4 Maxwell equation, now you have to just match PV is equal to TS. If this is T, this has to be S, this has to be V. If this is P, this has to be V. This is T, this has to be S. If this is V, this has to be P. If this is T, this has to be S. If this is T, this has to be S. This is V, this has to be P. Because ultimately we have to match, cross multiply, we have to match PV is equal to TS. PV is equal to TS. Okay? No, Tapasvi is a method, but that method is also very long method. It is a very short method. To write the Maxwell equation, we'll be using a very simple thing. We have to cross multiply. We have to cross multiply the terms, numerator and denominator. If you cross multiply the terms, you will be getting PV is equal to TS in all Maxwell equation. PV is equal to TS will be getting in cross multiplication. Cross multiplication of numerator and denominator. You will be getting this term for sure. So you just have to write P by T, T by P, T by V and V by T. You just have to match T to S, PV, then TS, PV, TS, PV, V, PV and TS. Whenever it is T by V, you have to put a minus sign. Bus. These are the Maxwell equation. Whatever is in the denominator you have to put here. Whatever in the denominator put here on the other side. The denominator on this side will have to be kept on the other side. The denominator on here has to be kept on the other side. Similarly, this is how you have to write the 4 Maxwell equation. So see, the 4 Maxwell equation you can write in just 30 seconds, less than 30 seconds. Okay. These are the 2 important relation: coefficient of volume expansion beta, it is equal to 1 by V of del V by del T at constant pressure, and isothermal compressibility is equal to minus 1 by V of del V by del P at constant temperature. These are 2 important formulas you have to remember. Maybe they can ask you to find these 2 terms directly by using this formula. Next is the TDS equation in differential form. This is also important, but I don't think that this is important for GATE exam. In differential form, you can write the TDS equation as CV dt plus T times of del P by del T at constant volume into dV, and TDS is equal to CV dt plus T times del P by del T at constant volume dV. Have you understood how to write Maxwell equation? Yes. In just 1 minute you can write all the Maxwell equation by just remembering this thing. Cross multiplication of the terms, you have to match PV is equal to TS. And whenever it is a ratio of T by V and V by T, you have to see a minus sign on the other side. Okay. Last term is Joule-Thomson coefficient. What is Joule-Thomson coefficient? Hi Divya Mishra, very good evening. Welcome to the session. Joule-Thomson coefficient is basically an experiment done by both Joule, who gave the first law of thermodynamics, and Thomson. They together have done an experiment on throttling process of a real gas. They basically throttled a real gas. ठीक है. So when they throttled a real gas, they have seen that they have come to know about a term called Joule-Thomson coefficient, which is equal to slope of temperature versus pressure at constant enthalpy. That is called as Joule-Thomson coefficient. This Joule-Thomson coefficient is equal to this for real gas. Real gas के लिए ये relation आती है. Real gas, it is equal to 1 by Cp of, the Joule-Thomson coefficient is equal to 1 by Cp of T times of del V by del T at constant pressure minus V. Okay, and for an ideal gas, Joule-Thomson coefficient becomes 0 for an ideal gas. It is 0. This question came in GATE exam in 2020. 2020. That what is the Joule-Thomson coefficient for an ideal gas? This simple question came in the GATE exam. Can you believe it? Joule-Thomson coefficient for ideal gas is 0. Okay. Here is the derivation for that. You will get this derivation in the PDF. I will send the PDF in the Telegram group, so you can download the PDF from there. Okay. Now Joule-Thomson coefficient for ideal gas is 0. Okay. So important thing that I want to tell you here is, in case of vapor compression refrigeration, that you study in the gas refrigeration air conditioning subject, we use throttling process, right? We use throttling process in the vapor compression because throttling process is an isenthalpic process in which temperature and pressure both will decrease during the throttling of a real gas to produce cooling effect. In vapor compression refrigeration VCRS system, we use throttling process, and so temperature pressure decreases and it produces cooling effect. But in case of gas refrigeration, we don't use a throttling process. Why? In case of gas refrigeration, we don't use throttling process for gas refrigeration. Why? The reason is very simple. Because in gas refrigeration, we use ideal gas. And for ideal gas, Joule-Thomson coefficient is 0. Or temperature, enthalpy is constant. As enthalpy becomes constant, the temperature will be constant. So there will be no drop of temperature. Temperature will not drop. It will be constant. If we use ideal gas and if we use ideal gas for throttling process, then you will not get any decrease in temperature. Why? Because throttling of an ideal gas will not cause decrease of temperature because for ideal gas, enthalpy is a function of temperature, and for ideal gas, temperature will not decrease. The temperature will not decrease for an ideal gas. Clear है सभी को? Is it clear? So that is why we don't use throttling process for gas refrigeration. We use an expander. So very important thing is that Joule-Thomson coefficient. See, this is a, sorry, I think I don't have, yeah, this is a graph. This is a graph of Joule-Thomson experiment. These are the different throttling curves. These are the throttling curves for different gases. So this is, let us say, gas 1, this is gas 2, this is gas 3, different types of gases. And what he has observed that when he was doing the throttling experiment, he found that initially when he started throttling, what is throttling? Throttling is a process in which pressure continuously decreases. During throttling. Okay, so pressure was continuously decreasing. Initially, before this inversion curve, there is a curve called inversion curve where the temperature becomes, at which Joule-Thomson coefficient becomes 0. Okay, inside the inversion curve, as you go inside the inversion curve, temperature drops. But before inversion curve, the temperature will increase and pressure is continuously decreasing. So in the Joule-Thomson coefficient, before inversion curve, the temperature rise will take place. In this region, temperature rise will take place. Temperature rise take place before inversion curve, in the right side of inversion curve, temperature rise take place. In the left side of inversion curve or inside inversion curve, temperature start to drop and pressure is also already dropping. So Joule-Thomson coefficient will be positive in this region. This region is called cooling region because temperature is decreasing, and this region is called heating region because temperature is increasing. So in the case of throttling of a real gas, before inversion curve or in the right side of inversion curve, there will be a heating region, and inside the inversion curve there will be a cooling region. Temperature will drop inside the cooling region and Joule-Thomson coefficient will be positive. And for an ideal gas, Joule-Thomson coefficient will be 0. So there will be nothing like cooling or heating. So the important conclusion is that Joule-Thomson coefficient is positive in the cooling region. That is, the slope of constant enthalpy curve on temperature entropy diagram is positive in cooling region, while it is negative in the heating region. There is nothing as heating or cooling in the for the ideal gas, and mu is equal to 0 for ideal gas. Joule-Thomson coefficient is 0. Last thing I have to tell you about Clausius-Clapeyron equation. Clausius-Clapeyron equation basically is this is the Clapeyron equation. It is basically used to find the, if you know the slope of, for a phase change diagram. Okay, so you know that in dp by dt or del p by del t is equal to del s by del v. By using one of the Maxwell equation, or by writing in this form, dp by dt is equal to ds by dv. Okay, so if you know the value of slope of a pressure temperature curve and you want to find the latent heat value, you can use this Clapeyron equation. Okay, in the Clapeyron equation you need, if you want to find the latent heat for a phase change process, you can use this Clapeyron equation. And this equation, this is the specific volume of the vapor, this is the specific volume of liquid. Okay, now if specific volume of liquid becomes very less than vapor, because we treat vapor as an ideal gas, and for ideal gas we can write its specific volume of vapor is equal to R into T by P. If you put this value here, you will be getting this equation. This equation is called as Clausius-Clapeyron equation. This is called Clausius-Clapeyron equation. Okay, so this is a very important relation. This is, you have to remember, Clausius-Clapeyron equation is used to find the value of latent heat if saturation pressure, temperature and the slope of pressure temperature curve is given. You can use this equation to find the latent heat for a phase change process. If the value of specific volume of liquid and vapor is given, then you have to find the latent heat. Then you can use this relation called Clapeyron equation. This is Clapeyron, this is Clausius-Clapeyron equation. Okay, so this is the last thing I have to tell you. Now we have compressibility factor. Compressibility factor is equal to it is equal to PV by RT. Okay, if this compressibility factor is equal to volume at any instant divided by volume at ideal gas, the further is, if the value of Z becomes 1, it is for ideal gas. For ideal gas, the compressibility factor is 1, and for real gas, compressibility factor is greater than and less than 1 for real gas. The more is the compressibility factor deviates from the ideal gas. Like if it is greater than and less than 1, then the gas will deviate from the ideal gas. If it is less than 1, it will be having negative deviation. Okay, if the real gas is, for example, if you see the deviation of an ideal gas, so hydrogen and helium have positive deviation. They have positive deviation from ideal gas. If this is the ideal gas, so hydrogen and helium has got positive deviation, while carbon dioxide, CO2, it has got both positive and negative deviation from the ideal gas. Okay, it has got Z greater than 1 and Z less than 1. So any gas which will deviate from both, which will be having both positive and negative deviation from ideal gas, if it is having a negative deviation, it shows that the gas is more compressible than expected from ideal behavior. And if it is having greater than 1, it is positive deviation, shows that gas is less compressible than expected from ideal gas behavior. There are some properties called critical properties, like critical temperature is the maximum temperature at which gas can be liquefied. Okay, critical pressure is the minimum pressure required to cause liquefaction, and critical volume is the volume occupied by 1 mole of gas at critical temperature and pressure. These are important things. Van der Waals equation is also very, very important. P plus A by B square into V minus AB, or it is equal to P plus N square by V square into A into V minus NB is equal to nRT. This is actually the ideal gas equation, Van der Waals equation. Van der Waals equation is the equation for real gas. You have to remember that. And this equation also very, very important. In this term, A is the correction factor for intermolecular attraction, because in the ideal gas equation you have done two assumptions. One is intermolecular force of attraction was neglected, and the other was that the volume occupied by the molecule was negligible as compared to contained volume. So if you take these two assumptions from the ideal gas and put it into the real gas, then you get this Van der Waals equation. Okay, so this is very, very important equation. In this equation, the unit of A is atmosphere liter square per mole square. This is the unit of A, and unit of B is liter per mole. Okay, this is very, very important. Very important relation is that on pressure volume curve, if you have to find the value of A and B in the Van der Waals equation, so you can find it with the help of these two relations. Because on critical isotherm, there is a term on critical isotherm, because on a pressure volume diagram, the line which passes from the critical point is called critical isotherm. This is called critical isotherm. Why it is called critical isotherm? Because it is a line which passes from the critical point. So for the line which passes from the critical point, it has got a point of inflection. Inflection means because at this point the slope will change, the curve will change its behavior, right? The curve will change its behavior after the inflection point. So at this inflection point the slope will be 0. So the slope of pressure versus volume at critical point will be 0, and not only the first slope but second slope will also be 0 at critical point because of point of inflection. Okay, हिंदी में बोलो बेटा कृष्णा पाटिल, इसमें हिंदी में मैं आपको क्या समझाऊं. एक्चुअली दिस इज अ चैनल इन विच वी स्पीक जनरली इन इंग्लिश, इसीलिए मैं इंग्लिश में बोल रहा था बिकॉज, लेकिन जल्दी ही हमारा हिंदी का चैनल भी बनने वाला है. फ्रॉम 2nd of January विल बी हैविंग अ मैकेनिकल मार्वल्स चैनल, ओके, इन विच विल बी स्पीकिंग इन हिंदी. ओके, सो इफ यू यूज दीज टू इक्वेशंस and you use one equation of this, if you use three equations, this equation 1, 2 and these three equations, you will be getting this value of critical temperature as this: critical temperature, critical pressure and critical volume. These value you will be getting, and if you put this equation from these two equations, you will be getting this value A as 27 into R universal squared into critical temperature squared divided by 64 into critical temperature. This is critical temperature value of A, and this is critical pressure. So this is how you get the value of A and B. Okay, A and B that are there in the Van der Waals equation, this value is equal to this: 27 into universal gas constant square into critical temperature square divided by 64 into critical pressure, and B is equal to universal gas constant into critical temperature divided by this. This is the result you will be getting. Okay, so this is all in the revision of thermodynamics. I know that मैं बहुत ही जल्दी किया और बहुत ही ज़्यादा चीज़ें करनी पड़ी, और 90 मिनट्स का टाइम हम लेके चले थे. वी हैव टेकन 90 मिनट्स टाइम, बट 90 minutes is not possible to cover thermodynamics. Now I have totally got it. Actually, that was my target, that I will complete the thermodynamics revision 90 minutes. That is not possible because thermodynamics is a very big subject. It's not possible to cover this in 90 minutes. Theoretically not possible. So that is all in the revision of thermodynamics. I have covered a lot of things from 7 p.m. till 10:20. It's around 10:20. So I would like to conclude the session now. And please, the PDF of this session will be available in our Telegram. This is our Telegram link. If you have not joined our Telegram group is Grade Up grade up ESE and GATE /ME preparation. You can join our Telegram group of grade up. In the Telegram group of grade up, you will get the update of the upcoming session. The upcoming session update you will be getting in the Telegram group. Okay. Also, I will send the PDF of this session. PDF of this session in this Telegram group I will upload that PDF. Okay. And tomorrow on 26th and 27th of December at 5 p.m. there is complete revision of fluid mechanics. Okay, on 26th and 27th, that is tomorrow and day after tomorrow, there will be complete revision of the fluid mechanics subject. Okay, at 5 p.m. timing you have to note down. The timing is 5 p.m. So I will see you at 5 p.m. tomorrow and day after tomorrow for the complete revision of thermodynamics. And on 28th December at 7 p.m. there will be practice session on thermodynamics. Where we'll be solving only the numericals of thermodynamics for GATE 2021. Okay, so this is a very, very important update regarding the upcoming sessions. And from 29th, 30, 31st, we'll be revising IC engine, refrigeration and power plant also. So everything will be covered, don't worry. So अब हम डिनर ही करेंगे, don't worry. Now we are going for dinner. और क्रिसमस के दिन था और क्रिसमस आप लोगों के साथ ही मेरा हो गया as expected. So इतना बोलने के बाद मेरे गले में भी अचानक से I'm having some pain in my throat also. So my dear students, Merry Christmas to all of you. That is my Christmas, we can say gift, or we can say Christmas. एक तरीके से I have tried to become a small Santa for you. That I have given the revision of entire thermodynamics I tried to give you the revision of entire thermodynamics in 90 minutes, but it was not possible, so it had extended to more time. Okay, so I'm going to see you tomorrow at 5 p.m. Okay, for the revision of fluid mechanics subject. 5 बजे लेक्चर होता है बेटा, 5 बजे लेक्चर होता है त्यागी. So my dear Tyagi, so you can watch the recorded session, no problem. Okay, but the lecture timing will be 5 p.m. because okay, that is already allotted time. Okay, so I am going to see you at 5 p.m. Thank you so much for joining me for this session. And if you have liked this session, please do not forget to give more like to the session. Share this session to your friends, to your colleagues who are preparing for GATE 2021. And the PDF of this session I will upload in the Telegram group, which is written here. So you can also download the PDF of this session. Okay. So thank you so much for joining me for this session. Please like the session, share the session and subscribe the channel. Thank you so much and have a very good day and Merry Christmas to you. Merry Christmas to all my dear students. I'm going to see you tomorrow. Thank you everyone. Now you can enjoy. Now you can enjoy and have your party. Yes. Thank you so much.